by RSG Brazil, a well-established student network recognized as a member of International Society of Computational Biology Student Council. The SIG aims to bring together Brazilian and foreign researchers in interdisciplinary scientific forum to encourage the scientific production of participants through presentation and discussion of the research currently under development. In the 2021 edition of the SIG is going to address the theme machine learning. We present the SIG machine learning in bioinformatics to discuss a sub-area of the artificial intelligence, which has led great advances in omics science, system biology, evolution, and structural biology. To discuss them, now we bring to you some excellent researchers. The meeting program will feature 5 international and national keynote speakers, students' presentation talks, and a virtual poster session that you can check on our website. We remind you that the poster session is going to take place through the event on the official website of RSG Brazil, where you can ask questions or contact people about the work in a chat below each poster. The certificate of participation is sent within 40 days after the event. To receive yours, you need to fill the forms that will be sent in the chat and that is available on the website. It is going to be open until the end of the event. In advance, we would like to thank our general supporters, the ISCB Student Council and the Brazil Association of Bioinformatics and Computational Biology, AB3C. So let's start. Our first speaker is Marcos Machado. Hello, Marcos.
Hi, everybody. It's a privilege to be here with you. Thank you for the opportunity to share our experience with this excellent community.
Thanks, Marcos. Marcos Machado. He is a medical physicist at Hospital São Rafael, Salvador, Bahia, and scientific director at RadTech. Marcos is master's degree in nuclear engineer at Federal University of Pernambuco and a PhD student in radiomics and artificial intelligence by the Federal University of Bahia, and had worked as scientific director and medical physicist for more than 5 years, leading research teams in telemedicine and artificial intelligence systems for medical diagnosis. Marcos will present the topic, integrating clinical features, image biomarker, and machine learning algorithms for precision medicine and clinical practices. Marcos, thank you so much for coming. It's a great pleasure for us to have you at this virtual meeting. I will give you the words.
Yes, thank you, Gisele, for the nice introduction. Okay, I expect that you see my screen, right?
Right.
So this is a project that we developed during this year. Actually, it started in 2020, in November 2020, and now we have the final results. That is technological development initiative, which we mean to integrate clinical features, image biomarker, as we will further call radiomics, and machine learning algorithms for precision medicine in clinical practice. The affiliations and the conflicts that I have to disclose is that I'm partner of RadTech, which was funded by FINAP during this project. So radiomics was highlighted as a hot topic in Nature in the recent years. And year by year, studies and researches about radiomics is increasing exponentially. So what's radiomics itself? Radiomics is a field of medicine that aims to extract image biomarker and use this image biomarker to associate with the disease. This association may be related to chemical process, physiological process, anatomic, and that have an impact in the texture of the image. And this then it could traduce a clinical process and associate the clinical process with the pattern of the image. Firstly, I want to introduce you what is a PAC system, a picture archiving and communication system. A PAC system is a repository of image that stores the medical image in a server. So this image must be ultrasound, maybe PET, computed tomography, X-rays, and so on. This project aims to develop a technology that is embedded in a PAC system. And so the doctor itself, in a patient schedule, a patient list, he chooses the patient. So when he chooses the patient, the system tracks the image into the pack, from the packs to the viewer. So in this viewer, the doctor interacts with the viewer, and then he can hear called the COVID diagnostic tool. So our development aims to embed into the PACS viewer system an intelligent diagnose support system. So we have to have in mind that our project is about technological development and clinical research. And okay, so COVID causes pneumonia. COVID-19 is a kind of pneumonia, right? When the doctor interacts with the image, he's not sure if the pneumonia finding is COVID related or not. So radiomics could provide additional support for the doctor to decide whether the pneumonia finding is COVID related or not. Because if he knows that is COVID related, he may anticipate some clinical decisions. This is a structured report in the medical community, is increasing the use of structured report because this is a way of standardization of clinical communication. So instead of using an open template for the doctor to report the findings, more and more it's being used structured reports in a standardized manner, right? So this is a standardized structured report for pneumonia, not COVID specifically, but pneumonia. Then we retrieved from the electronic report, okay, these features, and then we created an independent artificial intelligence model. And then further, we want to connect this independent model with radiomics. And then we have a multiomics model, okay? And then we would reveal mechanisms related to chemical, to physiological, and anatomical process, as I said before. Then we developed this model. The doctor chooses these options. From choosing these options, then the system in a back end, we assess an artificial intelligence model. We developed this part of the study. Let's have in mind that we divided our study in two stages, right? One first that is specifically for structured report, and another side specifically for radiomics, and then we join these models together. So this model is about structured report, right? We use 124 patients referred to pneumonia, 69 subjects with COVID-19, and 55 subjects with other pneumonia not associated with COVID-19. So these images were analyzed by 3 radiologists, and then we developed the model. And then we validated this model with an independent cohort. So this is the accuracy of our model in an independent cohort. One may say, okay, this is not different from the radiologists. Radiologists maybe perform better than this. So let's have in mind that we not aim to substitute the doctor reporting. We aim to helping to assist the radiologist reporting. And since our model was developed by experienced physicians, our model could help non-experienced physicians and could help residents and could help in doubt of some cases. So we embedded this system in a cloud, right? And if for our model, if it is less than 45% or score, it is not likely to be COVID-19. And if it is more than 55%, it is likely to be COVID-19. So this is an example of COVID-related pneumonia. And this is also an example of an explainable model. More and more, the medical community wants that the artificial intelligence model can be explained. And then we put here what is the odds ratio of every question. Then when the doctor marks these options and he has the score, he has an insight of why this case is COVID-like pneumonia, because the odds ratio um, for this feature is 8.6, and this the odds ratio for this feature is 9.1, and this is a language which the doctor understand odds ratio. And then this is a way to explain our model, why this model performed as COVID-19 like pneumonia. All right, and then the radiomics involves more complex image processing steps. We firstly want to decide which radiomic features we will use in our model. We use the PyRadiomics library to extract 93 radiomic features. And from these features, most of them are not reproducible or are too dependent on the equipment. And we use this technique using erosion, using blurring kernels. Erosion is like when the physician delineates the lesion, it is operator dependent. We don't want it to be operator dependent. We want that it is automatic and not dependent to the operator. So we use the doctor delineation, the three doctors delineations, to train a deep learning, a neural network to develop an automatic segmentation. Then we develop this automatic segmentation, and the automatic segmentation use the segmentation to extract the 93 features, and we used erosion and blurring kernels to simulate varying viewers, observers. Like erosion is like the physician delineates the lesion, and then we make artificial observer by erosing the lesion for 1 millimeter and erosing the same lesion for 3 millimeters. And then we perform the intra-class correlation coefficient to eliminate features that are dependent from this variation. And we also put blurring and sharpening kernels, and also performed the intercorrelation coefficient. And at the end, 12 features were selected using one specific that we call not interpolating the pixels, one specific method, and other specific method that is interpolating the pixels. In this case, we extracted only three features. So let's have in mind that from this whole process, we extracted only 3 or 12 features that was used in the study, and we developed an automatic segmentation. So we developed an automatic workflow for enhancing radiomic feature selection in computed tomography. And from this workflow, we have now an automatic segmentation, and we have now robust features, only robust features. We want that our features be independent, be robust, be reproducible. So that is what we achieved with this step of our work. And now let's have in mind this simple workflow in machine learning. Machine learning, you must have one subset for training the model and one subset for validating the model. So this is the first step, training the model. You cannot use the validation subset for like the segmentation step that we performed. The segmentation step that we performed, it was in the model building or training the model. The feature selection that we performed was in this subset, right? So you cannot perform this image processing, feature selection in this step. This step is only the subset is only for validating the model. So one group of patients for creating the auto segmentation, for selecting the radiomic features, for building the model in the same training data set. Let's have this in mind. And another independent subset, another independent group only for validating the model. This is not correct, okay? This B step. Training and testing in the same subset. This is wrong. You have to avoid, you cannot do this, right? Okay, so in the model building, the model training subset, we use 74 subjects, and we made a cross-validation method for training the infinite. The infinite is for training for auto segmentation and feature extraction. And then we used all the 74 subjects for model segmentation, feature extraction in the validation group. From the 74 subjects, CT image has many slices. So one image may have 500, 600, 400 slices. And then 74 and multiplied by this number is 8,000 slices. Okay, 8,000 images. We use a total of 8 to 10,000 images for training or neural network for auto segmentation. We then use the dot augmentation. Augmentation is needed because neural networks operates as better as more data you have. And we use the same technique for erosion to create new data sets. And we improved our model or segmentation model. The F1 score came for 89%, which is satisfactory. This is the result of our cross-validation result, patient by patient, in the model building in the training group, right? So for most patients, we had the old segmentation better than 70%. This is okay. Then remember that the feature that we use is not sensible for small segmentation variations. Okay, then after we have in the model training, the auto segmentation, we segmented the lesions, we extracted the radiomic features. Within the radiomic features, we can train our model. Then we trained our model with several machine learning methods like random forest, SVM, random trees, logistic regression, and so on. Then finally, we defined that the random forest performed better for our sample. Okay, this is the step which we use both models, radiomic and the clinical model based on structure reports to ensemble both models. We performed with a very simple decision tree, and then we have very good model with approximately 93% sensitivity and approximately 80% specificity, that in this case performed better than the radiologists. But let's have in mind that we don't want to substitute the radiologists. We want to help radiologists for reporting, to taking out, to help in critical cases. And this is our apparatus workflow. We developed one workflow that is a workflow for knowledge creation. We developed this infrastructure that now can be used for other imaging methods, for other diseases, which is the workflow for auto segmentation, radiomic feature extraction. And from this workflow, we embedded in a viewer the knowledge which the physician can interact. So in a innovation perspective, we have one workflow that can be provided as a service to create new knowledge for new diseases like lymphoma, like cervical cancer, and other imaging modalities like magnetic resonance, ultrasound. In this workflow, we develop the knowledge. We have an infrastructure to scale knowledge development. And this workflow where the doctor interacts directly with the knowledge. This is the interaction between doctor and the interface, the viewing interface. The physician chooses COVID-19 in this case. That could be cervical cancer, that could be other imaging modalities. And then he chooses these options. From choosing these options, and then he processes. By processing, they score, performs the structure report score, the radiomic score, and the enclosed score. This is the final result. In here, the physician knows that this case is more likely to be COVID-19. This product will be commercialized by the brand Nuclearis. And okay, that's it. I'm open for questions, and I'll be very happy to respond every question that I would know. If I don't know, I could search and respond afterwards. Thank you. Thank you for your presence.
Thank you, Marcos. Thank you so much for your presentation. It's very interesting. Was excellent in the lecture. And I want to ask you some questions about the software. Yes, the time for develop the process the all algorithm, the machine learning. It's long time. What's the bottleneck for this process?
Mhm. Yeah, we have a multidisciplinary team involved in this project. The all steps are complex, right? It's not difficult for bioinformaticians like you, but it is time consuming. Yes, it is time consuming because it is trying, testing, it's correct, it's not. We find pitfalls during this journey that we have to remodel or study design and doing uh, everything again and again. So we have in one part we have the technological development part, which we already had the viewer technology, the PAX technology, and we had to develop new features into this viewer, new features into this PAX system to support the new technology, the new machine learning technology. All right. So the view and the PAX had an effort to be done, and the machine learning specifically had another effort to be done. And the effort to be done in the machine learning step are the traditional ones. Firstly, the auto segmentation. uh, we didn't want that the doctor itself does the delineation. This is possible. This is done in many clinical facilities, many clinical settings and clinical situations. The doctor delineates the lesion, but this is not common. This is time consuming. Then we had the challenge that our product to be observed in the clinical practice. To be observed in the clinical practice, it doesn't have to be time consuming, or the doctor will not use it. And also, if the doctor does the delineation himself, there is a high risk of operator bias. Okay, then the step for training the neural network to do the auto segmentation is a specific effort. We need to have an infrastructure for image processing. We have a like simple, not so sophisticated infrastructure, but an experiment takes 5 7 days to train one neural network, and sometimes we have to train 10, 30 neural networks, and it would take you, let's say, for 5 months for training the neural network, right? And if you have a giant infrastructure with supercomputers, you can do it much faster. Okay.
Yes.
This is the step for the auto segmentation. The step for the radiomic feature extraction is relatively simple, as we used a very known library called pyradiomics. Then image feature extraction is relatively simple, but from using these features and selecting the correct features and building and testing the model is another effort. Then it is simple for bioinformaticians. It is simple for who know the steps that has to be done, but it is time consuming. That's what I would say from your question.
Yes. Yeah, we have another questions about the segmentation, the part of segmentation these images. How many types of image did you use for this process? You say that you use image from cancer, another disease. You know how many types of images did you use?
Mhm.
In the
Yeah,
if
for the
in the algorithm, the algorithm have some difficult to distinguish some types for example, cancer and COVID, or some type of cancer and some type of COVID. Some
Mhm.
you found this?
The neural network are specific for the task. If you have a different task, you have to train a different neural network. Neural network has the advantage that you don't have to train everything again. The network we use is, let's say, pre-built infinite. Okay, the infinite was previously trained by other groups. Okay, trained for lung and for COVID. Okay, so we started from this step. We used a subset, which we called in our presentation the modeling group, okay, the feature selection group, the same group, to retrain, not retrain, to input additional knowledge to this network, okay. But if I would use magnetic resonance for glioblastoma, I would have to train another neural network because the knowledge the Infinite already had was specifically for COVID, specifically for lung. Okay,
Okay.
and this study was for COVID-19. We used computed tomography images from COVID-19 patients and other pneumonia not related to COVID-19. Okay, this project. However, we developed an infrastructure, which we called Workflow One, an infrastructure that now, from now on, we can develop new models because the workflow is likely ready. We can develop this for other image modality, other diseases, because we acquired this knowledge and we have already the infrastructure already built. All right.
Right. We have some question. You have one question. Have Alexandre Pascal. Did you try to test another cross validation techniques?
No, we only tried the kind of cross validation that we use. That is the cross validation for auto segmentation. We did not use cross validation in the validation of the model. In the validation of the model itself, we separated the group. We did nothing with this group. Also validating the model because we wanted to know what was our model performance without inputting any kind of information leakage. There is a problem in machine learning. We cannot have information leakage. Otherwise, you will have overfitting, right? And then the cross validation step was a cross validation step to train the neural network for the auto segmentation in this in the training group. Okay, after we did everything in the training group, we and creating the model in the training group, then we validated the model in the validation group, which we did nothing, only validating our model. Okay,
Okay. Okay. Thank you, Marcos, so much for your lecture. It was very, very interesting. Thank you
it
for
is my
coming
pleasure.
here today. Okay.
Thank you.
Uh, Thank you. Bye.
Bye.
Now come back 9:50 for the second lecture with Dr. Emilio Fenoy. Okay. Hello everyone, we are come back. Following with our symposium, we are going to receive Dr. Emilio Fenoy. Dr. Emilio Fenoy is PhD in Biotechnology and Molecular Biology at Universidade Nacional de San Martín, in Peru, where did you work in development of machine learning models for the prediction of ligand-receptor interactions. Currently, he is postdoctoral fellow in Research Institute for Science, Systems and Computational Intelligence in Universidade Nacional do Litoral in Argentina. Dr. Emilio will present the talk, Data Representation for Machine Learning Protein Diabetes. Now I will give the words to Dr. Emilio. Dr. Emilio, there is a pleasure to have you with us today. Thank you for coming. We can start.
Hi, thank you very much for the nice presentation. Okay, I'm gonna share. Okay, can you look at my presentation now? So, thank you very much for inviting me to this symposium. It's really nice to be part of some events that are for students. And today I'm going to talk a little bit about data. I think this is not a very popular, maybe, topic. Let's face it. When was the last time you heard someone saying, "Yeah, I'm gonna be the next 4 months curing data and trying um, to put together a nice data set"? Usually, when we think about training a new machine learning method, we think about coming up with some nice architecture and apply it to a new problem and have some new insight on that problem. But it's usually not so easy. We have to spend almost half of the time looking at to have a nice data set. And it's a very important task because it's the base of uh, all the model. And if something goes wrong at this point, we will have to roll back and take back everything we did to address this matter and start over. So it's really nice to take some time and look at your starting data, just learn from my errors and my experience about that. Yeah, take some time to look at it. So if you study or work with machine learning, I'm sure you came across this phrase, garbage in, garbage out. And it talks a little bit about this. From bad data, you will have a bad method. And usually this is overlooked. Um, so this picture is nice because it has uh, this data that is disorganized coming in the analysis pipeline, and it came out sorted in some way because uh, the models nowadays are so powerful that they will fit anything, even if it's noise, and it will give some results. But sometimes those results are just not useful at all. And in the base cases, we will realize instantly that something is going on with that, and we will look back at our data. But sometimes these predictions look nice, and we go on with all the analysis, and at the end, we discover some error and have to start all over. So we make a lot of decisions in this process of how to process all this data that comes from different databases, that come from different groups and different assays, and in general, biological data is really messy. And we introduce some bias in this process. Um, So both cases are really problematic if we left out the data processing and we focus only on the model, the result is bad. And also the other way around, if we only look at data and leave out the model, the result is also bad. So among all of these decisions that we have to make and this bias that we could introduce, there is one that I wanted to talk in detail today, that is how we represent our data. So once we have our big, diverse, and non-redundant data set, we have to decide how are we going to encode this data. As we know, our data lives, it's from biology, and it lives in biology world, and it's composed by amino acids or nucleotides or just atoms if we are working with some smaller compounds. And we have to translate all that information into numbers. That is what the computer does. So how to do it? It's not trivial. There are many ways to do it. Every way has its problems, its drawbacks, and also have some strong points to be addressed. So now I want to talk to you about some of these and some cases. So the first thing that I work with when I faced this problem, I decided to use just two features to characterize. I worked with the entire proteins, and to describe them, I used some features related to them, some physicochemical features, as we use some physical features to describe a person. For example, if we look at the haze, the color of the eyes, the color of the hair, we can use also physicochemical proteins, features to describe proteins, such as the protein length, its molecular weight, hydrophobicity, disorder, so on and so forth. And we can translate this amino acid sequence or the molecule into a vector of different numbers and use those numbers to make some predictions. So we actually used that in a work from my master thesis some time ago. I don't want really to calculate how much ago, but we used this approach, translating all our proteins. In this case, we had the proteome from a parasite of cows from Africa. That the parasite is Theileria parva, and we have a subset of a bunch of proteins that were positive, that were antigens that started the immune response in the cows, and then a set of negatives that didn't do so. And we wanted to find in the whole proteome of this pathogen new proteins that could be used to make a vaccine that also had this property of being antigenic. So to do so, we calculated some features for all these proteins, and then compare the positive and negative sets with just the student test to get which of these features could be used to discriminate between the two groups, and then use just a ridge regression model to assign some weights to these features and try to recover from all the other proteins in the pathogen some candidates to be into the vaccine. And this type of approach, this kind of information, it's really nice because it's a high level information. We already are looking at things like expression or the subcellular location of some proteins, some characteristics that are not directly related to the protein sequence, but they have to be process in some way to obtain it. But it's also its main drawback, because some of these features must be obtained from the lab. So it needs some time and some resources to get them. For example, the expression data took a few years to be calculated, and some others can be obtained from existing models that predicts, for example, disorder or the subcellular location of a protein. But in those cases, we're using predictions to make predictions, and that can be a problem because we are adding error to the error. So even though this kind of approach seems really nice, it has some serious problems. So we decided to move from it and go directly into the sequence and try to encode the sequence and use a more sophisticated method like artificial neural networks, and try the network to learn from the sequence the features that are needed to predict some problem. In this case, we also moved to just trying to predict the binding of two molecules, one peptide and one protein. So it was also a little bit simpler, the task. And we started to play with some new ways to encode this information. So the first thing we tried, because it was back in 2016, was the popular one-hot encoding. It's really simple. It's used nowadays too. And in this case, what you want to do is to get all the possibilities that compose your data. In this case, since the proteins are just a string of amino acids, we have all the possible amino acids, 20 amino acids, and we encode it like with a vector of 20 positions, where every position is 0 except for one that corresponds to that amino acid. So to fit this into a neural network, you just encode all the amino acids in your sequence to its corresponding vector. For example, here we have a sequence of just two amino acids, alanine and leucine, and we have the 20 numbers for alanine being 1 and 19 zeros after that, and then the 20 number for leucine. So each of these numbers is fed into a neuron in the input layer, and you have the first 20 neurons in this network that modulates the impact of having each of these amino acids in that position. So the first neuron of the network will have an associated weight that will module the impact of having an alanine in the first position of the sequence, while the second neuron will modulate the impact of having a cysteine in the first position of the sequence, and so on. So in this case, we are just saying to the network which of the cases are in each of the positions. And it doesn't matter which is the case, it will train to fix all its weights to modulate each of these cases. So we used this kind of approach to make our prediction on peptide MHC class 1, which is just a protein from the immune system, and predict its stability. So we had a small peptide, usually 9 amino acid long, and we predicted given the sequence of this amino acid, if it will bind to the MHC and how long it will stay there. Of course, the composition of this peptide impacts greatly on how it will bind this protein. But this kind of approach have also a problem, that is its oversimplification. All these vectors that encode all the amino acids are, if we recall some mathematics, some old mathematics, they are orthogonal. They don't share any information between them. So we just know that they are different cases, and any pair of two amino acids are as different between them as any other pair of amino acids. So every component in this vector is not shared by any other vector. And we know that that's not true. The amino acids are related between them, and it's not the same to mutate one amino acid into another that mutate into any other. They have some common properties that are shared among them that let us, for example, group them into different clusters. And it's not the same to change a hydrophobic amino acid into a polar amino acid or into another hydrophobic amino acid. It's the same way with these big aromatic amino acids. If you change some small amino acid to one of these big amino acids, the mutation is very disruptive, can have a big impact into the structure of the protein and also compromise its function. So how we can measure this kind of relationship between these amino acids? Well, we don't. We just look at the biology, so we can learn from it. This was proposed by Margaret Dayhope back in 1978. She looked at some blocks of proteins that were highly conserved from the same families, which they are supposed to have the same function, and look at the likelihood of mutating an amino acid into another. So seeing in biology which mutations are allowed and which ones are not. And the idea is that if a mutation is really disruptive, it won't be allowed because the protein risks to lose its function. And you can put all these observations into a matrix that are the substitution matrix. I'm sure you came across any of these because they are really popular, mainly to make a sequence alignment, to measure the score of a sequence alignment. And they have all this information of the likelihood of changing any amino acid into any other. Of course, amino acids that share some physicochemical properties can be mutated between them because their impact in the structure and the function will be minute, while changing into different amino acids with different properties could be troublesome and they are penalized. We can see, for example, leucine and isoleucine, which are two amino acids really close, that have all in all the components similar values. When one have a negative value, the other does so, and also with the positive. So we can imagine in this 20-dimensional space that these two amino acids will be close between them. And both of them will be far away from for example, aspartic acid, which is a polar amino acid with a negative charge, and that have in its components big differences with these two hydrophobic amino acids. So to encode an amino acid using these kind of matrices, we just use all the raw, so all these vectors which are close between similar amino acids, and we can see this closeness between them by projecting these 20-dimensional vectors into 2 dimensions. We can see that they are forming some clusters in there. If we look at the properties of these clusters, we can see that, for example, red and blue that are positive, yes, negative and positive charged amino acids are close together, while the black and orange, that are hydrophobic amino acids, are on the other side. The orange amino acid that are these big amino acids with aromatic rings are also together, and the special case of cysteine that makes these disulfide bonds, and it's a really special case, is far from any other amino acid. So now we improved the one-hot encoding into another vector 20 amino acid that has some extra information on the properties of each amino acid. And we can do exactly the same, translate each amino acid into this vector and feed the network with the extra feature that we can now know or estimate the impact of having an amino acid that we don't have in our data set. Let's say if a position in our data has only leucine and isoleucine, and we want to predict some peptides that have valine in there, for example, in one hot encoding, we don't know what to predict because we never saw a valine in there. It's completely different from anything we saw. So we can't say anything about that, and usually we will just discard this peptide. And in this case, for example, if we see at the valine the last one of the amino acid in this matrix, we can see that also it's pretty close to leucine and isoleucine in its components. And so that mutation maybe will be acceptable, and we will consider that peptide as positive as well. So with this new information, we can make better predictions and even predict over data that we don't have any insight in. And we use that also to make a little bit more sophisticated method in 2018. And also, as the previous one, it was at the moment the state of the art of the prediction, in this case, of phosphorylation sites. So it's similar. We wanted to predict that a kinase will recognize and phosphorylate some position using this approach to encode our data. So having this, what's next? These were two very simple approaches, even though they work. Now we use some new and even more sophisticated methods. So instead of the traditional way of using this feature extraction, either by calculating features or even taking these matrices that are also features to train a model, nowadays with deep learning, the philosophy changed, The people just try to feed the, the network with something really raw and let the network to make its own representations in all these layers. So it usually goes from more abstract representation in the first layer, and then these abstract representations are combined until you get your final result. Um, so it changed the paradigm from giving something already processed to the network to just let the network to do its work. And this can be applied also to our problems in biology, because most of these networks are used in two main problems, which are images and natural language. And we have both of them in our data. The primary structure of a protein can be seen as a sentence where each amino acid is a word, and we can use some strategy from the process, the natural language process. Um, and the structure, as we seen in a PDB, like points in space, can be seen as a 3D image and use the techniques used to process those kind of images to process the structure. So in this case, we just use the primary structure because it's easier to obtain. We already have some of those. It's not so easy to get good structures. So we use the popular models to process this natural language processing problem. So one of them is the long short-term memory, which is a recurrent network that is fed with an input at a time. So in this case, it will be reading the sequence, one amino acid at a time. It conserves a state that has all the information in all this reading, and a lot of gates that would module the information that goes into that state. So if we want to add some information or forget some information, it depends on all these gates. And so this is one of the most popular models to use. And also we have transformers, which are a little bit newer, and also they are getting more attention than the LSTMs. I'm laughing because they use self-attention mechanism to read all the data. And instead of looking at all the input one at a time sequentially, they can just look at everything, and with this self-attention model, address the context and make also a prediction. And for this feature, they can be trained in parallel, so they are easier to train, or quicker to train than an LSTM, and so they are becoming the main thing to use in this kind of problems. So in this case, we just looked at 12 different models that try to encode proteins using these strategies. Most of them are from the last 3 years. We have from 2019 and 2020, most of them. And one thing that it's a common feature among them is that they are training an unsupervised way. So they use a large corpus, like all the proteins in UniProt, and then use that to feed the network. and try to predict the same sequence that they use as input in like an autoencoder way. And they use different strategies to do so. So this is mostly what they do. They use a given sequence as an input, and then try to predict the same sequence. In this case, SEGVEC, which is one of those, use a convolutional neural network as the first layer, but then they feed that into two LSTMs that goes forward and backward. So they don't only learn the amino acids that they are seeing, but also they learn the context in, of that amino acid. So we have even more information, not only having the difference of having one amino acid in a position, but also this same amino acid in another position maybe have another impact. And this can be done, as I said, using each amino acid as a word, or using peptides of different lengths as different words. But the strategy is the same. And the idea is that once you have this model trained, as they do, you can then use it as an encoding, as we did before, just using to predict the representation, the vector of numbers, and feed it into your network, or as part of the network in what is known as transfer learning. So you put this already trained model before your network, and you retrain it with this new task that you want to address. So it fine tunes the weights in the model. And this is really useful that you can incorporate this to a given task. So as I said, this kind of models learn just in a supervised way from the data, the properties of the amino acid. You can see here, this is also a projection of one of these methods. And you can see that also can learn the properties of the amino acids and can cluster them according to them. But also at seeing the context in where they are embedded, they can predict also things like the secondary structure. If you have your proteins predicted with these methods, and you cluster them, you get all the proteins that are rich in alpha helids in a cluster together, far from the proteins that are very enriched in beta sheets, for example. And that's because they can merge all this context data. And also, they can give some insight into the function of the proteins and some other more high-level stuff. So we were really interested in this kind of embeddings. We had a project to apply them into. So we wanted to find one that was nice to us to use. So we take our data set and we try them. So for example, in this plot, we have our data set, our proteins converted using, in this case, SEGVEC, and plotted with UMAP. We made a projection in 2D. And then we just painted them according to the PFAM domains that they have to see if this given embedding can obtain the information regarding the domains and can group these proteins together. So we selected some cases that were interesting to us. For example, the blue and orange domains are two immunoglobulin-like domains, so they participate in the immune system, and they are close in structure, so they should be together, and they are, even though we have a small group here, because these proteins have also other domains, so they are a little bit far away, but most of them are in here together. Then also we get some protein kinases. These PFAM domain have mostly serine and threonine protein kinases, while this other, the red one, have a tyrosine kinases, and also they are grouped together up in this plot. And the rest of the domains were selected because they are rich in alpha helix or beta sheets, or they have a combination of both, like these brown and purple groups. They are both domains, transmembrane domains, very rich in alpha helix. And even though they are not so close, they are in the same part of the plot, while the other, like the blue and orange that are most enriching beta sheets, they are on the other side. So this was just to have some visual input on how well this method performed. But we were shocked when we saw all of them. And even though some can perform this task right, like SEGBEG, ESTM, maybe ProtTrans a little bit, some of them doesn't have a clue of what's going on, and they just put everything together and in a big soup of colors, or even make these spaghetti-like things that doesn't make any sense. So it was all right. We have some visual insight on how well this could be, but we wanted to measure it and put it a number to decide. So we got our hands in our data, which is a subset of a kappa 3 challenge dataset. We narrow it down because it's really big. It's like 67,000 proteins from more than 1,700 organisms, and it was a lot of data to work with. So as this was an exploratory assay, we reduced that to Homo sapiens proteins only, and we set a length threshold of 700 amino acids, because one thing that is really cumbersome of this method is that they are very demanding in terms of hardware. They are really time consuming. So our task to do it was to predict the gene ontology terms. So gene ontology, if you don't know about it, it's a controlled vocabulary of genes or gene products. It has its attributes annotated. It's divided in 3 sub-ontologies, which are cellular component, molecular function, and biological process. So any protein in this dataset has some tags regarding of its attributes. They are organized in a tree-like manner. So we have at the root of this tree the more general attributes, like cellular component. It's just they are inside the cell or around the cell in some way, and there is no information in there whatsoever. And then when you go down this tree to the leaves, you have more and more specific terms. So in this example, we know that this protein, it's in an organelle, that it's a membrane-bound organelle, and if we keep going down, we find out that it's inside the mitochondria. And it depends on how much we know about this protein. We can have tags from above or below this tree. So our task is to predict all these tasks for a given protein. The first approach that we took was a very naive KNN, where we have a query protein here represented as a star. Let's say it's the first protein here in the list. And we measure some distance in this embedding space. We take neighbors from there and assign the tags of the neighbors to our query protein, and we say that those are the gene ontology tags of that protein. So to measure this, we use two different measurements. Recall, which will just measure how much of the actual tags we are getting by looking at the neighbors. And this is it's important to us because if we get consistently near the 100% of all the tags of our query with its neighbors, we can reduce the space search from the 9,000 proteins that we have in our dataset to just a few neighbors. But also we calculated the F1, which has into account also the false positive rate. So we can calculate not only how many positives that we have from our query, but also how many noise we comes with these neighbors. How many tags not related to our query also come. So we made some plots for each of these methods that we were testing, and we found out that they are very different in the results. We have some clear winners here at some extent, like ESM. And then we have a small cluster of several methods altogether. But there are also some methods that perform really bad. Even though this is cellular component, that it's known to be one of the easiest tasks to do, the nice thing is that almost everybody reach around 90% of the positives with the only 10 neighbors. So we have here the neighbors that we are taking in and the measurements that I explained in the last slide. So in another sub-ontology, like the molecular function, we have also the same trend. The same methods are having a good performance, while others are having a bad time. And this is also kind of implied in the sequence. We can, let's say, we can use there is a relation between the sequence and the function, even though it's not so linear. It's so easy to make that association. Still, we still can have some nice results. And then we have biological process, which is just a problem because similar proteins mostly with these methods that look mainly at structure and amino acids, it's really hard to find in which biological process they are participating, because similar proteins can participate in really different processes. Like, for example, kinases, it's a case where they all are similar. They perform the same task to phosphorylate, but they are all over the place modulating a lot of processes inside the cell. So even though they can be close in structure and sequence, they are far away in the biological process that they participate in. So looking at these methods, looking at which ones were above these measurements, we can see a pattern here. Most of them are the ones that use transformers and LSTMs. These two, especially, well, these three, if you want, that use BERT and ELMO, are the best performing methods. And then another method that use like convolutional neural networks or another types of recurrent neural networks are usually below the expected performance. So having these results, we just tried one last thing, that was using the methods to train a multi-layer perception. So we set up a very simple network using ReLU as the activation function and Adam as the optimizer. And we try to predict all these tags using the embeddings. And again, the trend it's still mainly the same. The methods using transformer and LSTMs are the best, while the others fall a little bit behind. Still, by using the network that allows to combine all this information, the worst methods come up a little bit. They gain a little bit of performance, but still they are behind. And if we see at the critical difference plot down below, we can see that in some cases, like here in cellular component, that it's easier to predict. All these methods that are better are clustered together, so the performance is not significantly better. But in some harder tasks, like this molecular function or biological process, ESM have a significant advantage over the all other. So the last thing we saw is what happened if we go down the tree. So the first few tags are easy to predict because they are very popular and they are in almost every protein. So you have a lot of examples to learn from, and also are very general. But in the more specific attributes, you have less data, and also they are harder to find. But we saw that in these plots, if you go in the x-axis, it's the depth, and then in the y-axis, you have the F1 value, and you can see that ESM, the model that we saw, it outperformed every other method maintains its advantage all over the place. Um, so that was everything we did regarding this. Now we want to train a new model using all this information that we took and look at how better we can do in this CAFA challenge. So some final remarks I wanted to say. It's, well, there are really a lot of ways to encode biological data, and every way has its pros and cons. You usually have to look at the how much you gain by going into some more complex representation. The one hot encoding, for example, is really simple, really quick, and has less information. But if it's enough, maybe it's best to use it rather than a big embedding like these ones that we saw at the end, that are extremely time consuming. You need a GPU, because if not, it takes days to make just the embedding, the prediction of the representation. So they are really hardware consuming. So usually you have to just see your options and select the one that it's better for your problem. There is no best solution, and usually test all of them and decide which is best. So, well, I want to just thank to our group, to my PI, Georgina, which is really a nice mentor, and Alejandro Herrera, which is a partner in this project, and it's just I think it's a robot. It's really a hard working guy, and then all the group at the sync, which is always there to brainstorm and to help with any problem that there is. So thank you. I'll be taking any questions that you have.
Emilio, it was a very great lecture. Thank you very much for coming. It's very interesting. We have some questions about the lecture. In structural biology, we have new advances when we relate it to machine learning and deep learning. In your vision, what is the perspective in this field, in structural biology? What is the perspective do they apply machine learning, deep learning to the protein?
Yeah, I think that's the new way. Uh, those methods that I showed are all of these last few years because they found out that they can use all this stuff to do biology. So they are applying it a lot from these 12 methods. I think 8 of them are from these years, and they are still coming out. So I think it's a really powerful tool, and it has a lot of fields to apply into in bioinformatics.
Okay. Okay. About the disciplinary, the groups of it's basic questions about the multidisciplinary in this area. It was a great, it's popular, it's great perspective, it's great, it's it's great vision that you come about the interdisciplinary biology, mathematics, and physics working together in this area.
Sorry, come on. I had some problems with the audio. I
So,
think.
okay. Now it's about interdisciplinary in this area by informatics. What is your perspective? What do you think about this in this machine learning and deep learning?
Well, it's really necessary. I mean, I work in and I think everybody doing bioinformatics work in an interdisciplinary ambient. We have some biology that have their insights on the small details, all these tricks that in biology, and some guys from the other way in informatics that knows all the newest methods and how to apply them. And I think you need both perspectives to get a nice method. As I said at the beginning of the talk, it's some nice data set, and I think that mainly the task of all the biologists part of the group, which tries to get a comprehensive, diverse, non-redundant, and nice data set to start with, and then some hard informatic guys to apply all these crazy networks to get the most out of them.
Okay, another question. How do you ensure you are not overfitting with a model? It's about the your. How do you ensure you are not overfitting with a model?
Are we sure that we are not overfitting at all? If there is a way to know that you are not overfitting, it's really hard to do that. But we use cross validation as usual. Also to make the partitions instead of randomly separate the data, we looked at the protein sequences. So all the sequences that are similar, they go into the same bins. So there is no data leakage between these bins, and also use some other regular strategies to try to get rid of all the overfitting possible. But I believe that always you get at least a little bit of overfitting. It's too many parameters, and at some point these networks had to overfit. The thing is to maintain that level of overfit below a reasonable level.
We have one question, Thiago Minuzzi. Regarding deep learning in bioinformatics, what area do you think deep learning can help the most, and what are the ones deep learning may not be that is useful?
In my experience, I think deep learning can be used into the most convoluted problems. Like we use them to use our entire proteins to learn some things that are not directly related to the sequence. For example, like the function or the biological processing where they are involved. So these tricky questions, I think, are best for deep learning. Also, dealing with structure. We now that all these structure from AlphaFold came out, we are trying to use them to extract some information, and using deep learning, it seems to be best. But there are some problems that are rather simpler. And actually, for example, this interaction between a peptide and a given protein, we just used simple, shallow neural networks, and with some tricks on the biology part, uh, we just got the best performance we could, and no any other deep learning model could surpass that. So it depends on the complexity of the problem, I think.
Okay. You said about the problem with the field data and the similar protein to fit the model. Uh, what is the most problem when you fit your model? The similar proteins when in the same family, or you have few proteins with different families
So
for fitting your model.
uh-huh, for fitting my model. If no, I just got a problem with the audio. Could you
Ah,
repeat?
so
What just?
you said about the problem with the field data,
Uh-huh.
okay? What is the most problem? The field data when you need to fit in the model, or when you work with similar proteins to fit the model.
If I don't know if I'm understanding right the question. If you have uh, only a few, a bunch of data, or if you have a lot of data but they are very similar, something like
Yes,
that.
your data is very similar. When you have protein very similar, you have some problems to fit the model, okay?
Sí, sí, sí. Yes.
Yes. But if you have more very similar proteins, okay, in your data set, but in another data set you have few data, but more heterogeneity
Mm.
proteins. What's the train data you can work with? What is the best fitting? What is the best results?
I'd get the few data but more diverse, I think, over the having lot of similar data. It always depends. It's not so
Yes.
black and white. But if you have diversity, maybe you can apply some strategies to get your data to be bigger. Like there are some, I don't recall the name, to enrich your data set with introducing some noise or something to get more examples, some synthetic examples. But I think from diversity, you can learn more than having a lot of similar data that usually we take like they are the same practically. That's why we put everything that is very similar into the same bin to train, because we consider that uh, they are um, redundant data. So that I take the less number but more diverse data set.
Okay. Dr. Emilio, thank you very much again for your presence. Thank you very much for coming.
Thank
Uh,
you all.
Thank you. And we return with the next lecture, 10, at 10 p.m. EM, sorry. Now, the last talk in this morning is with Dr. Nicola Bordão. Dr. Nicola Bordão is Bachelor of Science in Biotechnology at University of Padua, PhD in Structural Bioinformatics and System Biology in Universidad Pablo de Olavide in Sevilla, Spain. Currently, he is postdoc research in Bioinformatics and Computational Biology at University College London in English. Dr. Nicola Bordão presented the talk Exploiting Protein Structure and Family Data to Explain the Impacts of Genetic Variation. Now, I will give the words to Dr. Nicola Bordão. Thank you too much for coming, Dr. Nicola.
Well, thank you very much, Giselle, and thank you very much for the kind introduction and invitation. I mean, on behalf of Cristina Orengo, which is my PI and president of the International Society of Computational Biology, I would like to extend her thanks and her congratulations for all your hard work in organizing this. It's been an excellent symposium so far. So my talk today, it's on exploiting protein structure and family data to try to explain the impacts of genetic variations. So it's gonna we're gonna touch 3 different topics. The first one is gonna be how we are using deep learning strategies to expand cath protein family data. And then we're gonna show you how representative cath of protein domains in nature. And last, how we can use domain families to understand variant impacts. So I don't know how many of you work in proteins in the protein field, but just to give you a brief introduction, usually we get protein sequence data converted from genomic analysis, and it gets classified either at the sequence or at the structural level. And while the sequence is also informative for certain type of analysis, structure is almost always best. And protein folds are how this protein sequence fold in 3D space. It's actually much more informative. So whenever we look at protein folds, then the chemical nature of residues in the pockets and the surface patches that are on the outside of the protein, it's what dictates the function of a protein. So cath, which is our research maintained by us at University College London, gathers protein chains from the protein data bank on a weekly basis. And then we chop these chains into individual and constituent domains, and we classify them in a hierarchical classification where we look at the class, the architecture, the topology, and then finally the homologous superfamily of this particular domain. We do this based on the presence of very conserved domains and structural cores in these domains, and where, while some additional embellishments, they vary across species and across orthologs and paralogs, but the structural core is almost always conserved, not only across all these proteins, but across also species, even if they are very far away from an evolutionary standpoint. So we are able to capture around 90% of PDB in cath, and we classify them into 5,500, roughly some 5,000 evolutionary superfamilies. And in total, we have 500,000 domains with the latest release of cath 4.3. So in order to do this, the vast bulk of the work is done by some very old machine learning-based methods based on SVMs, where we look at, and we have an automatic remote homolog detection platform that tries to subclassify the chopped domains as soon as we get them into cath. And for the remainder, we have some manual curators that they look at cases that are particularly borderline. But in sequence data, it's also very informative. So our way to expand this treasure trove of information that we have in structural domains, we gather every single protein superfamily relatives, we encode them into a sequence profile, and then in a needle Markov model. And then using Hammer in our Gene3D resource, we scan all the UniRef 90 sequences against this 69,000 HMMs that we have. and we are able to give them a tentative assignment based on certain thresholds that we identified in the past. So this is able to bring from 500,000 domain structures, we're able to assign some of these to 150 million domains in UniProt, leading to a 300-fold expansion in the data. So whenever we classify this superfamilies, though, we have certain superfamilies that we call mega superfamilies that, while the core is very much conserved, we have all these structural embellishments, and all these things, they change the function of the protein ultimately. As you can see, the core is very well conserved here, but it's present in all three of them while having three completely different functions. So in order to try to have a deeper insight in these massive superfamilies, we subclassify these Cath superfamilies into functional families, or FAMFAMs. So we start by taking every single sequence that we assign to these domains, and then we do an HMM versus HMM comparison, and we build a tree of relationship across all these FAMFAMs. And once we have the completed tree, which sometimes can be massive, we have a tool called FAMFAMer that goes and tries to cut the tree in order to get the largest possible alignment that has still some coherent function into it. So we are able to do this using HMMs. Now we are trying some new approaches based on machine learning and embeddings, and I will try to explain that later on during the talk. So how FAMFAMer works is we look at the actual alignment in this case, and we can determine two different types of positions in the alignment, where we have certain residues that are conserved across two different functional families. And these ones are very conserved all across the alignment, mostly because they are very important for the actual folding and packing of the protein. And then we have some other ones that we call the specificity determining positions that are important for function. And these ones, they're what differs one particular FAMFAM to the other. And using FAMFAMer, we're able to scan through all these alignments and cut them into coherent subset of functional domains. At the moment, we have 220,000 FAMFAMs, varying a lot in both in size and in if they have a structural available. And now we're trying to expand these ones with every sequence that is coming in. Okay, so FAMFAMs, this particular way of subclassifying proteins, it's been proven with some analysis that we did in the past that they're not only very well conserved across these residues, but also that from a structural standpoint, all the residues that are actually important for function, like something that is associated to a binding pocket or to an active site, it's very, very close structurally. Even just by looking at the mean root mean square deviation, you can see that if we compare structures across an entire superfamily, we get on average around 5 or 6 angstrom RMSD, while for FAMFAMs, we are much closer than that. So once we have this information, then we, since we have these HMMs also for functional families now, we use this evolutionary information for function that is encoded in the FAMFAMs to try to give a functional assignment to proteins of unknown function. So every 2 years, there is the critical assessment of functional annotation, which is a friendly competition that where we benchmark all these different predictors. And Cath FAMFAMs, apparently they work very well because consistently we're ranking the top 10, and with the latest version, which is Kappa4, it still hasn't come out officially, but we saw that we rank among the top 3 for molecular function prediction and biological process ontology prediction. So even though there are new and novel methods that are based on network analysis or on machine learning, we can still see that evolutionary superfamilies, they still carry a lot of functional signal in there. Okay. whenever we look also at this particular FAMFAMs, then we can see if this particular residues, they co-localize in 3D, and we are applying this particular information for looking at disease mutation. We have a side project called FAMVAR that classifies all human disease mutations in cancer, part of the TracerX project. So our current approach now is based, we're trying to expand this new concept of FAMFAMs by treating sequence in a different way. This is an ongoing collaboration with the ROST Lab at the Technical University of Munich, where we are using a protein language model from deep learning, and we are encoding all the amino acid sequences into embeddings, where each one of them is represented by a vector in a hyperdimensional space. And we're using this to try not only to see if our FAMFAMs are coherent or if they could be improved using these methods, but we're using it also to predict other things just by looking at what's the distance of a particular vector in three-dimensional space. One of these, we can see that also these particular distances, they are very useful for determining functional associations. Whenever we look at what's the distance of an embedding within a superfamily, is generally much higher than when we compare a FAMFAM in this case. In this case, we are in this publication with Maria Littman from our group, from his group, we try to see how well this particular method fares in trying to predict enzyme codes, and we can see that we get a higher kind of coherence, even compared to FAMFAMs. So our latest method, which is going to be based, it's based on all of the subsequent analyses that are going to show from now on are based on this new predictor made by FAMSI in our group. It's this new remote homolog predictor that is based on these language models. So while before we used to have these very old SVM methods to try to assign a particular sequence or a structure to a given superfamily, now we are just taking the plain sequence, we encode this into an embedding, and then we use it to predict this particular superfamily. And we can see that even compared to other method like BLAST, or I don't have it in this particular plot, but even for HMMs, the performance is much, much higher. And we get around 80 to 90% accuracy almost all the time. So we can also see here that sometimes we have certain domains that we can't really predict, and we are able to bring in now using this new method. So this kind of ends the first portion of my talk. Now I'm going to show you how using CathE, which is this new predictor that we developed, how we are able to expand the data in Cath, and how representative is Cath of all the protein domains that are available in nature. So, as you probably know, and it clearly made the news when it came out, and it clearly ruined a lot of people's summer holidays, including mine, that DeepMind released AlphaFold for the public, and additionally, they provided 3D models for all 21 model organisms. And luckily, we know that they're planning to release models for the whole of UniRef, not by Christmas, as it was originally intended, but now they're going to release it in the spring. So we're going to have 3D models for around 190 million sequences, which is going to be a game changer, especially for organisms that are not model or not as well studied. And the fact that they gave this tool available for everyone, it means that even small labs that they lack the 3D structural capabilities to characterize their organism of interest, they can now try to have an insight on their particular biological problem. So all this data now, it's also available through Elixir, which is this infrastructure backed by the ISCB, and it's where we collate all these structures from PDB, from all the different data banks, into something that can be accessible from your laptop using a client. So DeepMind uses this this new method for predicting structure, and it it changed completely the field from one day to the next, because on the CASP, which is this critical assessment of structure prediction, it came in and it outperformed the second best match by almost twice the quality. And at first, when it came out, it wasn't released to the public. Most of the people, they tried actually to replicate what they saw they were doing, like a model very similar to this is Rosetta Fold from the Baker Group. But having it available, and now there are new Google Colab Fold Python notebooks that you can use online or installed on your cluster, and you can run DeepMind AlphaFold 2 like they did in CASP 14. So as you can clearly see, the critical the median free modeling accuracy increased dramatically in the latest versions of CASP, and now we are seeing such an accuracy that sometimes is actually superior to 3D models. Of course, all this information needs some sanity checks, mostly because all of these are predictions. These are not actual structures coming in, so we need to take into account regions that are of low quality or things that have intrinsical disorder in them. So what we did in the past couple of months, since AlphaFold released this treasure trove of almost 300,000 domains, is try to see how much of them we can assign to a known structural domain or a known superfamily. Because whenever you look at this particular structure, it could look like a bowl of spaghetti. You don't really know, based on previous knowledge, what it looks like. So, but using some of the tools that we developed in-house, like Cath Resolve Hits, we can scan this particular structure and its sequence against our HMMs, and then we can try to see if it falls into some predefined categories that we already kind of identified in the past. So some particular portion can map to an actual structure that we already have in Cath. Some others, they map to a PFAM domain that has a sequence domain but doesn't have a relative structure in Cath. And then we have something that is completely new that we call new FAMs. So using all this information that Cath Resolve Hits basically takes all these hits from the HMMs and tries to find what is the best non-overlapping domains that we can assign to a particular sequence. This gives us some particular confidence in doing these assignments. So what we did is to kind of identify on each one of these particular structures if something was already classified in Cath, so we can kind of bring it safely in. Something that is belonging to PFAM, that is not mapping to Cath, but then we can still try to validate using structural methods. And then potentially we have these portions in blue, that these could be completely novel folds or something that we haven't seen in the past, that we call new FAMs. So one way to do it is we use this new Cathy ANN method that I mentioned before, where we take in just a sequence of these structures, we encode them into embeddings, and then we predict its Cath superfamily. We use a very strict threshold, so we take only hits that have a 5% error rate. And then once we have these tentative assignments, we do a structural comparison. So we first consider that we have 300,000 and more domains to check in this particular case. We're going to have to use a very fast method first, try to see if we can get something immediately assigned. And then if we have some borderline hits, we are using some slower methods such as TM-Align or SAP on what's the 100 closest relatives by looking at the sequence embedding distance. And once we do these assignments at the end, it's kind of a cascading method. So we go from Cathy, then we go from FoldSeq, we go from Cathy to FoldSeq, and then TM-Align, and then SAP. And at the end, we actually have a result. It could be a Cath superfamily, or it could be something completely new. Well, some of these things it's a putative new superfamilies, because some of the things we noticed is that lots of these new things that don't map to anything, then we look at it and it's something that has a very low kind kind of structural quality, or it has very long stretches of intrinsic disorder. So whenever we look into this, we need to do still some manual curation for these results. So basically, based on this particular analysis, you can see that AlphaFold actually helped us expand the amount of knowledge we have on human protein domains by a good chunk. So as you can see here, we have around 15-20% of cath experimental structures. So something that it's an actual 3D structure coming from the PDB, and then we can bring in another 40%, more or less 40-45% using the HMMs that we can also cross-validate using the AlphaFold models. And then we have all these new portion here, another 25% that we can assign both using CathE and the AlphaFold cross-validation, or something that is just assigned using CathE. And this leaves us with this question mark, which is around a good 10%, that we could have low quality models, we could have disorder models, and we can also have potentially new folds. So, but as you can see, AlphaFold changed the game because it gives us, it's allowing us to cross-validate some of these results, while at the same that we already knew before, and at the same time, it gives us some good insight now on things that were unknown before. So one of the caveats with this is this particular model quality I was discussing before, because while we can see that cath domains, so things that we can bring into cath, they're very well conserved, and considering that these things are usually domains that are spread across multiple organisms, multiple species, and entire superkingdoms, it means that the multiple sequence alignment that AlphaFold is kind of fishing on to build this model, it's very deep. So it carries a lot of information into it, and the model quality is generally much higher. If we do the same for PFAM, we can still see that we have a slightly larger tail of low quality for some of the models, but still a very high proportion of models that have good quality. And then if we look at new FAMs, you can see that this is all over the place. So we have some things that it's just bad modeling by AlphaFold, and sometimes we can see that this is just because these particular new FAMs, they come maybe from one small organism that doesn't have a lot of relatives in the databases, so we can't really build a decent MSA. But there is still some signal of things that are highly modeled very, very well. But then we can also, there are probably some disorder regions here and there. So this is where the interesting stuff is. So whenever we look at the quality is actually one of the biggest issues we have been noticing. So while everything that in cath we consider everything that is characterized experimentally as a good model, then we have a look at all the hits that we can map regardless of its source. So in this case, HMMs or CathE predictions, we can see that a good proportion, almost 45% of these predicted domains, they fall with different level of model quality. So we can see that around 25% is very high quality. And then we have the vast majority of them, they are on medium, so something that is still borderline. And then we have some portions here that this one could account for things that are low quality or high intrinsic disorder. And we can see this whenever we look at more organisms. In this case, you can see that this distribution is more or less conserved across all these organisms. So, well, what's remarkable, though, is that besides expanding a lot some of the information we already had for human, and maybe Arabidopsis here, there are certain organisms that are completely kind of, I would say, missing in cath, like Leishmanian phantom here, but the small proportion of things that we can bring experimentally, it's almost completely shadowed by things that we can bring using HMMs and these new models. So now we're currently in the process of finishing all the 21 organisms. We have data for all of them, so we should have all these results available soon, probably not in the main cath resource, but something probably as a sister resource, that we're going to make these models and these chop domains available for the community very soon. So, okay, now let's go back to how many new superfamilies do we have? How much of this is actually something that makes sense from a structural standpoint or not? And so whenever we go to the end of our cascading protocol, we have all these leftover domains that we weren't able to assign to a superfamily. So we use the gain-fold seek to compare all of them and see if they actually fall within a certain distance between themselves. So we used it as a clustering method. And we were able to come up with around 530 superfamilies. This is a very, very rough estimate, and we're still going over these results because we're still kind of setting some internal thresholds for what is a good subscore in this particular case of what is an acceptable threshold for disorder or model quality. So this is a number that is going to change in the future, but this is just an initial rough estimate. This is also a bit limiting because we're only considering things that fall within these 21 organisms, and that's it, and nothing more. So while probably all these numbers, they're gonna change whenever AlphaFold is gonna release the whole of UniRef 90 in the spring. So one thing then we need to consider disorder particularly. You can clearly see that we have almost the same pattern as before. So cath domains, they generally tend to have a low disorder percentage, while PFAM tends to be mostly disordered. And then we have a very long tail in both PFAM and UFAMs for disorder. So this is something that we need to kind of set a sensible threshold before we can consider bringing these domains into cath in the future. So as you can see here, one of the analyses that we saw, these are some of the candidates that are part of these 530 superfamilies. And while some of these particular conformations, we haven't seen them, so it means that we don't have something looking like this in cath at the moment, there is this huge portion of intrinsic disorder on that cover most of the structure. So this could lead to a badly modeled region or something that is going to pack in a different way whenever it comes into contact with another protein. So this is kind of the current data that we have at the moment. So that's why manual curation is very important for this kind of data. So whenever we kind of filter out most of these, now we see that some of these are kind of, we are able to reduce it even further. Now we have 177 that we think are tentative new superfamilies, but as I said before, this is going to change. Using SAP, we were able to kind of do some structural alignments in an all versus all fashion between them. So we were able to kind of reduce these numbers even further, just to something more manageable. So one thing that we did as soon as we had these domains, specifically for these 21 model organisms, is that while cath-fam-fams, we have a large amount of them, cath-fam-fams are kind of based on the assumption that every single one of them has at least one relative with an experimentally characterized function. So we know for sure that this is an actual functioning protein somewhere. But the problem is that less than 10%, they have a structure within them. And using AlphaFold data, we were able to massively increase the amount of fam-fams that now have an actual reference structure within them. Just to remind you, this is how we do it. So we look at this conserved patterns of domains, pattern of residues across these different sequence alignments. And then we were able to expand almost all organisms. You can see here with, while we had some distant coverage for using just experimental structure, then we're able to expand human by another third of fam-fams that now actually have a structural representative. But in certain cases, we are able to cover almost all of them. If you look at here, like Arabidopsis or yeast, this one's AlphaFold literally gave us the upper hand, because now we can actually have, whenever we do a functional assignment, that we have an actual good model that then we can use for further analysis. So we can also see, as I mentioned before, that FAMFAMs basically they have they are having the same issue as AlphaFold in this particular case. So we're able to bring in a model if it's a particular superfamily that has a lot of signal. So if it's something coming from just a small subset of bacteria or archaea, this particular function that is found in that specific organism usually doesn't have enough sequences to be the good model. As you can see here, we can see that most of the model quality, the low model quality ones, they are in FAMFAMs that have less than 100 sequences within them. So we can also see that that's one of the issues is that not only having not having few sequences is a problem, but also having fewer species. So sometimes large FAMFAMs come from large superfamilies that are highly diverse also and found across multiple superkingdoms. But whenever we look at the number of taxon IDs within them, all the ones that have more low model quality, they all come from very, very specific organism-specific kind of functions. So, and this ends our analysis on AlphaFold. I mean, these are still kind of tentative results, and we wouldn't know. We will know the final counts for all these organisms probably in the next couple of weeks or so, since we're testing different thresholds and parameters for the various structural aligners tools that we're using. And now I'm going to start the last portion of my talk, which is about how we can use all this information, and potentially in the future, we can use all this AlphaFold information that we're slowly bringing in for how to use this information on how to understand variant impacts. So one of the first things we did, this is we just published the preprint last week. This one was a collaboration with the Baker Group that when the first version of AlphaFold came out, AlphaFold wasn't available, so RosettaFold was able to kind of try to mimic and improve on their previous methods, such as TR Rosetta. And using something very similar, we were able to kind of isolate all 500 human disease proteins that have no structures or homology models available for them. Kind of AlphaFold threw a wrench in our plans a little bit because while we focus on only 500 proteins, they will use the whole load for human. But it also means that it helped us cross-validate all the RosettaFold predictions. So what we did, we took all these 500 models, all these 500 proteins, and we modeled them using both AlphaFold and RosettaFold. And all these ones, we looked in the PDB, and they had no structure available, or the sequence similarity was too low to have a good homology model. So we were able to map these ones to around 700 FAMFAMs, and probably some of those now they're going to have AlphaFold models within them. And some of them, they were also coming from PFAM FAMFAMs, where basically we take PFAM family information, and then we use the same FAMFAM protocol that we use on cath sequences, and then we create some PFAM FAMFAMs. So using all these models, we were able now to kind of explain 1,000, which is almost 76% of all the mutations that occur in human. And we can see some interesting results, because you always think of AlphaFold as the panacea to solve every single problem in structural biology, but we can also see that sometimes using a combination of both can be good, mostly because most of the time AlphaFold has a better model, but there are certain occasions where RosettaFold actually performs better. And this is due to the fact that RosettaFold, besides using the multiple sequence alignment information, it also uses some other things like end-to-end learning and different techniques. So having different tools in your pocket can help answer more structures, actually. And we can see that while for cath, where we have all this information that is representative of very large multiple sequence alignments, AlphaFold being based on multiple sequence alignment is performing better. This operand that they have over Rosetta fold slowly goes away whenever we use things that have less signal, like PFAM, or even more with the new FAMs, where we have almost an even split between the two models, between the two methods. Apologies. So one thing that we did, as soon as we got this information and we know on which FAMs they map into, all this information that come from this specificity determining positions, all these ones we know that they fall very close to unknown functional sites. While almost all these proteins that we characterize now, they had at the beginning they had less than 0.1% of functional sites that were characterized in the literature or in other databases. So we used our own internal pipeline, which is called cath-fun sites, and to cross-validate this, we used two more methods. One is called P2Rank from the Hosker group, and another one is MetaPPISP from the Zoo group. And these two, they work in a kind of a complementary orthogonal fashion, as they used ligand binding information, and this other one uses protein interface residues prediction to calculate if something it's an actual functional site, where if we disrupt the active site with a mutation in this particular pocket, is going to affect the protein functionality and potentially lead to disease. So we were able to subclassify all these structures in different classes. We can see that there is still a portion that is still unexplained, but for some of them, we can see immediately, we can kind of pinpoint with accuracy what is affecting and why is it going to cause a disease in human in this case. Sometimes this mutation, they, for a good chunk, for 30%, they affect protein-protein interface residues. Sometimes they affect the ligand binding site. Sometimes they affect both. And sometimes they are just affecting some of these conserved residues that are very important for folding. So sometimes these ones, they fall into highly conserved residues, and these ones, they just affect the overall structural assembly. So using these tools, though, can lead us also to different kind of predictions in this particular case, because if we just limit ourselves using one method or the other, we would miss some other information. So in this particular case, with AlphaFold, we were able to identify a core set of residues that are in the ligand binding sites. And this protein is a putative sodium-coupled amino acid transporter. And any mutation in any of these 8 mutations, they can lead to foveal hypoplasia, which is a kind of retinal problem. And we are not able to find this particular set of mutations using Rosetta Fold. While using Rosetta Fold, we're able to find some other mutations that are particularly interesting in this other protein, where we have mutations associated to this protein that can lead to this disease that is called MEDS. So this particular, I hope I'm convincing you about that FAMs basically are very useful for doing all sorts of analysis, because all this information, all evolutionary information that is conserved across them is very powerful. So the next one, and it's going to be the last portion of my talk, it's kind of a serendipitous, I would say, considering all the circumstances about COVID, kind of collaboration that we started in the early month of the pandemic. It was a whole 1 month, like a whole rush from start to finish, just from starting from the actual raw research idea to having the paper out. And so we used this functional families information to predict what is the host range of COVID, because at the time, there's still some uncertainty about it, but the general consensus is that SARS-CoV-2 was originally a bat virus, and then it was transmitted to a pangolin and eventually to human. But one of the biggest problems with this kind of viruses, whenever they turn endemic, like it's happening now, is that since they use a very common receptor, the ACE2 receptor that is found in almost all animals, there is a huge risk that the mutations on the receptor on other species are not enough for the virus not being able to infect them. And if the virus can bind potentially to these proteins, it could go into hiding and then eventually mutate and come out again later on in the future. So this particular process was guided by the fact as soon as the whole genome and the proteins of COVID they were released, we did a quick match. We did a quick scan using Hammer, and we noticed that all the human ACE2 proteins fall within the same superfamily, within the same family, which means that it's incredibly conserved. While they fall within the same superfamily as expected, the function and the residues that they are conserved across all the different species, they don't mutate enough for it to be falling into a different family. So the initial idea was to try to see if we can model all these different mutations in all this model, in all these, in all the ACE2 proteins that were deposited on the ensemble at the time. And this number has now grown, but at the time it was 215. So we were interested in seeing if we mutate the residue in the human SPIKES2 model, which now we had a structure at the time, can we see how destabilizing these mutations are? Can we see, okay, after how many mutations in ACE2, the spike is no longer able to bind because it's too destabilizing. So our way to do it is we not only initial analysis, they use some contact binding residues, just some of them. There were 8 residues, but using the information coming from the FAMFAMs, we used all these SDPs, these specificity determining residues that we found before, and these ones we noticed that since they are very important for a function, we included them in our analysis. So this gave us more information to work on. And additionally, for all, besides the contact residues and these SDP residues, we took also all the residues that were within 5 and 8 angstrom of this set of residues. This gives us around 32 residues that we can look if they mutate or not in different species. So these particular residues, we would expect, since this particular superfamily is very conserved and this particular family is very conserved, whatever we do look at is that this subset of SDPs, if we have a mutation in here, potentially could be very, very destabilizing. And this was the case. So we fed all these 215 models that we generated and its corresponding set of mutation that would make them different from human into MCSM PPI2, which is a tool that predicts the effects of mutations by looking at protein-protein interactions. And then we try to figure out what is a good delta G value for discriminating, okay, SARS-CoV-2 is going to potentially infect this human or not, this particular animal or not. So we mutate all the human residues into the human structure, and then we saw what were the results. But in order to cross-validate these things, we noticed that we had a long distribution of changes in this stability, and we noticed that some organisms that we'd expect to be very close to human, that we expect to be potentially susceptible to infections, like the big apes, that like gorilla, orangutan, they could be affected by SARS-CoV-2. We were interested in seeing that actually bat, which originally was thought to be the source of SARS-CoV-2, actually had a very high delta G. So it means that potentially by the time it jumped from bat to pangolin to human, now it has mutated enough that it will be tough for it to go back to bat. So in order to find a good threshold for this, we had this collaboration with Jo Santini, which she's a microbiologist, and she spent a good 3 weeks just going through all the rush of literatures that was coming out during that period. And she was checking if some animals, they were actually getting infected. So by using this experimental data, we were able to validate our predictions. And so we set our threshold at 2, and we can see that basically horseshoe bat is our lower limit. So anything that it's below 2 delta G, it's something that is potentially a risk, and something above it could be safely excluded. So once we have a look at this, then the correlation is good. We can see that the experiments, they actually detect infection on almost all of them, that they kind of fall below this threshold of 2 that we set. Well, there are still certain experiments that didn't kind of corroborate our thesis, but this was just an initial kind of view on this problem. You could also mutations also on other receptors like TMPRSS2. They can also lead to this kind of having something that, even though the binding with the ACE2 receptor is good, there are other effectors down the line that could affect how and if SARS-CoV-2 infects these particular animals. So we came out using this combined information coming from the FAMFAMs and the infection data, come out with this visualization of how an animal could be at risk of catching COVID. And we noticed that most animals from zoos, they can actually be at risk, especially monkeys and apes. But in the home environment, we noticed that dogs, cats, and hamsters, all these ones, they could be at risk of having it. And weirdly enough, sheep has the same set of residues as human. So it was a huge problem here as a concern in the UK. As we know, we have lots of sheep. So this should be the end of my talk. So, but in conclusion, I hope I convey my message that AlphaFold models are very good for increasing the amount of structural information we have in functional families. And potentially with the release of UNIREF 90, is going to increase dramatically the amount of knowledge that we have on almost all sequences available. And nearly 90% of domains, now that we have these new machine learning embedding methods and AlphaFold, we can bring 90% of domains in CAD, more or less. And the remainder are either low quality models, or they are highly disordered, or from small species-specific families. And lastly, the structure, all this information that we get can provide a very good rationale for functional impacts of genetic variations, both in human disease, but also on SARS-CoV-2, like I showed you. And with this, I would like to acknowledge everyone in our group. I mean, this was the first time we saw each other after a year and a half. It was the first time we went to the pub together. And with this, I'd like to thank also other collaborators that we had, like Sudat was an ex-student of Christine, how he has his own group at the University of Malaysia, and everyone at the Technical University of Munich for their help with the CATHI predictor, and Marty Steinegger, Stephanie Kim for helping us using their very alpha version of FoldSig to do these assignments. And with this, that's the end of my talk. Thank you very much.
Thank you very much, Dr. Nico, for the nice talk. It's very good, very great, very interesting, excellent talk. Thanks so much for coming here.
Oh, no problem. It was a pleasure.
I want to ask you about the cafe. It's available? It's a perspective to become available soon, or it's how is the perspective you all lab?
So it will be available because the trained embeddings, they're already available through the ROS Lab group. So you can potentially just get embeddings from them, get the cath data, and train it on them. But we're planning to, well, I mean, that's always the plan, you know, but we're planning to publish the preprint before Christmas for that, because all the AlphaFold analysis are also relying on that. So we need to send the CATHI preprint out first, but it will be before Christmas, I think.
Thank you.
No
in the algorithm that you use in machine learning, the main physical chemical features that they classify the protein for analysis to predict? How the main predictors?
I think I do have, let me see if I have another slide. We noticed sorry, I'm trying to figure out if I think I had a slide and I deleted it. Probably it was good if I kept it actually. Okay, give me a second. Sorry, it's Okay. No, I think I removed it. Apologies. But basically, one of the ways we do to predict this, we use a whole lot of different information. So we use ligand binding site. We used context similarity in networks. And then we use all this. We have almost 60 different set of features that we consider. And then we use an XGBoost kind of method to kind of rank it and then get the best prediction out of them. We noticed that I think ligand binding information is one of the most ligand binding information and sequence conservation and pattern of conservation across the alignment are the most informative ones that we use.
Okay. And for the drug design, the use of the allosteric protein is very increased in the studies. I want to know if the CAF3 studies these allosteric proteins because the functional site is not in the core evolutive, more conserved core, but in another part of protein. So CAF3 had some line of search for these allosteric proteins to predict these spots.
So not us specifically, but the Rose group they just published a preprint, I think, a month ago, where they made this new predictor that looks at if a particular, also based on embeddings, if a particular region of a protein is going to bind specific small molecules. Besides small molecules, they also did another predictor that predicts if something is binding to DNA, for example, or if it's in a PPI interface. So it's more kind of just by looking at the similarity between embeddings, they're able to do this kind of predictions. But yes, there are models available for this.
Proteins, yes.
We're doing something. Well, we're doing drug discovery for SARS-CoV-2, but it's still not published at the moment. So the idea behind it is that we're taking, back at the beginning of the pandemic, the Krogan group, they made it all this map of interactors of human host proteins that were interacting with human disease, with SARS-CoV-2 proteins, and then we're looking at all the interfaces for those. And that one is going to be probably released early next year, I think.
Oh, great. And about the SARS-CoV, the COVID, the problem with the new variants. So you and your group test the CAF3, some variants, some mutation that it's similar that the mutation that we have today, like Omicron, the new concern variant.
So
what's in the perspective? It's good, it's bad.
Well, I wouldn't know, and probably also the general consensus is still too early to say anything about it, to be honest. But there is one of the resources that actually uses that we're collaborating with. It's called Aquaria, and I'm going to put a link in the main chat. Basically, it's kind of a protein structure visualizer where you can look at. Actually, I think I can probably share the screen because I'll probably make it quicker. So this is a resource that we collaborated with and we generated at the time. Am I still sharing my screen? Yes, I guess. Can you see this?
No.
Oh.
Can you? No. Can you share?
There we go. Sorry. Share this one. Okay. So this is called Aquaria. Can you see it now?
Yes.
Okay.
Yes.
Perfect. So this is a protein resource is called Aquaria, where we made a structural coverage map of all the virus. So here you have all the regions that are covered by known structure, and then in dark you have the portion that haven't been crystallized yet. And then here you know how many structures they actually interact with this particular protein in human, how many of them they with this one, if it mimics certain proteins, if it hijacks a certain process, or if it binds some particular small molecule. So it's nice to check, but then basically all the time you can also go back to the main structure. I mean, it will probably take a while because there are lots of spike structures available at the moment. But you can also see here a whole set of predictions. You can see if it maps to a cath domain, and then you can click it and it's going to highlight it. But one of the new features that we put, there is a preprint out now, that you can specify the set of mutations in the URL, and then you can actually see it. There was an actual tutorial by Andrea, which is one of our collaborators, and she pointed out all the mutations that you had in the Omicron variant on Aquaria. And then this one you can just kind of zoom in and do any kind of oh gosh, I think I messed it up. Anyway, so this one is Aquaria. Basically, you can also see your 3D structure using your mobile phone and augmented reality. So it's interesting for SARS-CoV-2, basically.
Yeah. Thank you very much for the lecture. It's excellent. I want to thank you again.
No, thank you for having me. I mean, I know I'm not Christine, so.
No, it was excellent. We're glad to hear in our symposium. Now we finish the morning part of the symposium, and we start at 2:20 p.m. Okay.
Welcome, my name is Pablo Fonseca and I will present some results about the
Hello. Hi, everyone. Welcome to the second part of our event. My name is Tayana Tavares. I'm a chair of the Special Interest Group 2021 with the theme Machine Learning in Bioinformatics. I would like to thank you very much for joining us in this afternoon. And I would like to remind you that we have the poster season on our website. You can ask and comment in the chat below each poster. And please don't forget to subscribe to our YouTube channel to know more about events and new contents about bioinformatics in general. Okay, now we are going to bring you our first speaker in this afternoon, Dr. Antônio Pedro Camargo. Hello. Thank you for your participation.
Thank you.
Dr. Antonio is biologist and PhD in genetics and molecular biology from Universidade Estadual de Campinas. Currently, he is a scientist at Joint Genome Institute in California. And Antonio presents the lecture, You Can Move, but You Can't Hide. Identify and mobile genomic elements across Earth microbiomes. So now I'll give the word to Dr. Antonio. Thank you again for being here. And
thank you. And thank you for having me. Just one quick question. Is the lecture going to be in Portuguese or English?
You can choose.
Okay. Is there any English speaker? And
we can ask.
Okay. No, I can present it in English though. Yeah, that's fine.
Okay. You can share your.
Yeah, just one sec. Okay. Do you guys see my screen?
Okay, it's okay now.
Okay. So yeah, thanks again. Thanks for having me. My name is Antonio, and today I'm going to present you about my current project. And the name of my presentation is You Can Move, but You Can't Hide. Identifying mobile genomic elements across Earth's microbiomes. Well, the first thing that I wanted to say is that for a long time, the idea that genetic information is vertically inherited in this tree-like format has permeated biology since Darwin first came up with the theory of evolution by natural selection. So this is a figure by Darwin himself, where he shows that genetic information flows from the ancestor to its offspring, and so on and so on and so on. So we could interpret the life on Earth, the history of life on Earth, using this tree-like pattern. But actually, nowadays we know that life doesn't work like this. Life keeps surprising us. So now we know that gene flow not only goes from the descendant to offspring, but also flows across different branches of the tree of life via a process known as horizontal gene transfer, where the genetic information breaks the species barrier and flows through from one species to the other. And this kind of genetic flow is much more widespread than people once thought. It is involved in the biogeochemical cycles. For example, viruses that carry genes for photosynthesis. They carry these genes from one cyanobacteria to the other and increases the rate of photosynthesis. And as you all probably know, cyanobacteria are the main producers of oxygen on Earth. It is also involved in ecological interactions when they carry genes for pathogenicity, for example, and also big evolutionary leaps. My favorite example is that the gene that is responsible for allowing nutrient transfer between the mother and the children in their placenta is of viral origin. So without a viral gene, placental mammals wouldn't exist. And yeah, horizontal gene transfer occurs by several mechanisms. The three most common ones are transformation, transduction via viruses, and conjugation via conjugative plasmids. And there are also some non-canonical ones, such as vesicles. The bacteria create and they carry pieces of their chromosomes. Then the tubes that also transport pieces of the bacterial chromosomes, and GTAs. Those are my favorites. They're pretty cool. They look like viruses, but instead of carrying viral genomes, they carry pieces of the bacterial chromosome. Yeah, but today I'm going to focus on my talk on mobile genomic elements. And what are they? Today I'm focused on viruses and plasmids. And they are biological entities that encode information that allows them to move from cell to cell, but they don't encode information to allow them to reproduce by themselves. So they're not living beings by themselves. They just jump across different cells and reproduce within those cells. When infecting a cell, both plasmids and viruses, they alter the genetic repertoire of their host because they introduce novel genes, like the example I said before. Some phages are bacterial or archaeoviruses. They introduce photosynthesis genes into their hosts. And when they alter the genetic repertoire of the host, they influence the host ecology and evolutionary dynamics. So despite their functional importance in biology, we still don't know a lot about the diversity and functions about MGEs. For example, the vast majority of plasmid sequences still comes from the genomes of isolates of bacteria or archaea. As for viruses, we know more about their diversity because there's a growing interest in uncovering viruses from environmental sequencing data, or metagenomes. I'll talk a lot about metagenomes today. But most of those projects focus on a specific environment, for example, the human gut. You'll find lots of papers talking about the virome of the human gut, or specific virant taxa. And I said that because the bottom line is there's still a lot to be discovered about MGEs. So in IMG, we host a database called IMG. No, I'm sorry, in JGI, we host a database called IMG that currently holds around 27,000 public metagenomes for an environment distributed across the Earth. And those metagenomes encompass more than 19 billion scaffolds. So we have a lot of environmental data out there from metagenomes from around the world, but we can detect MGEs from them. And by detecting MGEs from those environments, we can explore how diverse they can be, the different strategies that they can have, different genetic repertoires that they can have at a much larger scale than what is currently available. So, as you would expect, due to the main topic today, I'm going to talk about machine learning. Because to identify those MGEs within metagenomic sequences, I'm relying on machine learning. The goal here is to train a model that will be able to learn patterns that define and distinguish an MGE from non-MGE sequences. When I train this model with a set of sequences that I know that are either MGE or non-MGE, it will learn those patterns. And then when I feed the model with data of that I don't know whether those sequences are MGs or not, it will classify them for me. So as you guys probably know, the most important step and the one that you spend the most time in when you are working with machine learning is gathering a good and reliable data set. In my case, I started working this in April and it's December now, and I just finished doing it. So yeah, I gathered a data set comprised of around almost 800,000 sequences from host chromosomes, plasmids, and viruses. So host chromosomes would be my non-MGs, plasmids and viruses would be my MGs. And then my classifier is going to classify now environmental sequences into one of those three classes. And to maximize diversity, I did not use only sequencing data from isolates, viral isolates, plasmids isolates, or host chromosomes isolates. I also retrieved sequences from curated metagenomic data, which greatly expanded the diversity of my data set, the sequence diversity of the data set. Okay, so I'm going to talk about the model itself, the model that we designed to classify those sequences. So this data, the training data, was used to train a classification model to identify MGs, and this model uses two different sources of information. So from any given sequence, the model will identify genes and use the gene content of the sequence to tell whether it's more likely a virus, plasmid, or a whole sequence, but also a sequence-based branch that would that will only use the nucleotide sequence itself without relying on genes to do this classification. And then the outputs of both of those branches are aggregated. And then you have a final classification. So I'll start with the sequence-based branch. So neural networks can model biological sequences pretty well, and they can identify important features without human input. And this is especially cool for viruses and plasmids because we truly don't know a lot about them. Okay, we do know not a lot about viruses, but there's still a lot to be known. So the cool thing about some neural networks is that they can learn features that define what is a virus or what is a plasmid by themselves. I don't need to input features that I preconceive. And this can reduce bias due to human knowledge. So this is a very non-biological example, but I think it's interesting to try to explain this concept. So neural networks using natural language processing, that's a field in machine learning, can model contextual information and identify relevant segments in text data. So in this paper, they trained a natural language processing neural network to classify reviews on Yelp. And the reviews could be classified into positive, negative, or neutral. And then they started to explore the model itself to see, what does the model uses to tell if a given review is positive? And then they realized that the model learned by itself that words like enjoy, love this, my favorite, much fun, great food, those are words that indicated a given review is positive. But they didn't tell this to the model beforehand. The model learned by itself. And you can apply this in biology. So this is a paper. So this is a figure from a paper where they are showing that you can embed nucleotide protein sequences in the multidimensional space, and you can separate protein sequences, whether they are soluble or membrane bound, using just a neural network without telling beforehand what are the features that define whether a given protein is soluble or membrane bound. And so the sequences on the left are just a mock example. They're not real, but what the model does is it identifies some features in the sequences without you telling it that are indicative that a given sequence is membrane bound or soluble. It is a bit more complex than that, but that's the gist of it. The neural network will identify what makes a given protein soluble or non-soluble, and I can apply this to my data. So in our classifier, I use an iGLUE network, which is a kind of network that is really good to model sequence data, and I trained it to maximize the separation between the three classes, so hosts, plasmids, and viruses. So what the network does is it takes as input the sequence of the nucleotide sequence of each contig, and then it will embed the sequence in a multidimensional space and will maximize the distance between the different classes. So this is a real projection of my neural network. I omitted plasmids here because plasmids are they overlap a bit with the whole sequences, and they would make the figure harder to see. But yeah, you can see that the model did learn how to separate host sequences from viral sequences without me telling it what makes a host sequence host and what makes a viral sequence viral. The other branch of the classifier, as I've mentioned before, uses gene content to tell apart MG sequences. So even though MGs are very diverse, different types of viruses use different approaches to go from cell to cell, they have totally different lifestyles, they do share some common motifs. For example, mobility, as the name itself tells, those are biogenomic elements. So genes that are involved into those basic MGE functions, like the MG lifestyle, can be indicative that a given sequence is an MGE. So the first thing that I needed to do was to identify MGEs, was to identify those MGEs. I had to build a set of protein family models that are HMMs that can detect genes that are informative for classification. So in this case, here down below, I just put a simple example where if I find a contig that has one protein that was annotated as being a protoprotein, another one as a tail fiber, another one as a base plate, another one as a capsid, this is certainly a virus, because only a viral sequence will encode all of those structural viral proteins. But to construct this data set, I didn't want to only rely on public HMMs datasets like PFAN and Eggnog. So on top of getting gene models from those existing datasets, I also constructed new protein families by clustering millions of metagenomic proteins. And then in the end, I had a set of 1.5 million different HMMs. The next step then is to identify which ones of those are informative for classification. And the ones that are informative for classification are the ones that are specific to one class or the other, right? So in this case here, all of those gene families, they are relevant for identifying viruses because they're specific to virus. It's very unlikely to find a tail fiber protein that is a virus structural protein, anything that is not a virus. So the goal here was to identify which ones of those HMMs were specific. And what I did was I used those HMMs to search the proteins from my chromosome, plasmid, and viral data. And then I counted the number of times each HMM appear in chromosome, plasmid, and virus proteins. There was also one step of normalization where I downweighted matches to overrepresented taxa. This was a big problem. Why I was doing this? Because, for example, almost half of the plasmids in NCBI comes from the family Enterobacteriaceae. That is a family of bacteria that lives in human gut. And because they are human pathogens, and they're also lab models, they are overrepresented in sequence databases. But I didn't want my data set to be good at only identifying Enterobacteriaceae plasmids. So what I did to avoid this taxonomic over bias was to downweight the count to overrepresented taxa. If I got time by the end of the presentation, I can explain how I did this because I think it's pretty cool. Okay, so as I said, markers were then selected based on their prevalence and specificity, especially. By prevalence here, I mean how common they are, because I don't want to select a marker that is virus specific, but it will only appear in one virus out of the 500,000 that I have. I need to get a balance between having a good set of informative markers, but also not using a million different markers, because this would make the classifier very slow to execute. And I'm executing it in more than 20,000 metagenomes, so I need it to be fast. So after selecting the markers based on prevalence and specificity, I got a set of about 75,000 markers. And I am representing them in this figure in the right. So the color of it, so first thing, each circle here is a HMM, a gene family marker, a gene family model. And the color represents the level specificity. The lighter it gets, the more specific it is. Things that are in this corner are very plasmid specific. Things that are in this corner are very chromosome specific, and things in this corner are very virus specific. And one very interesting thing about those markers, is that I checked how many of them matched at HMMs with non-functions. So I did a HMM versus HMM search against PFAN and PTB, which are data sets of things, HMMs with non-function. And I found out that almost 3/4 of those 75 markers don't match any domain of non-function. And this fraction increases for the viral markers. It's even larger. So this is pretty cool. And because those genes with unknown function are very useful. They're very informative for viral and plasmid identification. The other thing I did, and this is just to make the next slide clearer. I classified those markers into 9 different categories depending on their position in this ternary plot. So the ones that are in the edges are the ones that are very super specific to one of the 3 classes. So those are virus specific, VV, chromosome specific, CC, and plasmid specific, PP. But there are also some that are very plasmid specific, but they also appear in some viruses, and I call them PV. The plasmid specific that also appear in some chromosomes are PC, and so on. Just so you can see, there are some plasmid markers here that also appear in some viruses. Okay. So for each sequence, the fraction of genes assigned, for each sequence that I'm trying to classify, the fraction of genes assigned to each of those specificity classes is fed to a decision forest that will classify the input based on the marker content. So what is a decision forest? First thing, what is a classification tree? A classification tree is one data structure that takes an input and makes a series of questions to this input to try to tell you what that is. So, for example, this is one of the trees in my decision forest. The first thing it asks for the sequence is the fraction of PPs of plasmid-specific genes in the sequence more than 0.2%? If yes, it then asks what is the coding density of the sequence and so on. It makes a series of questions so that by the end of the tree, the levers, that is the final outputs, are pure. They will only contain one class. So if your input sequence followed this path of answers here, by the end of it, you will know that it is a plasmid. But one single tree is not very reliable. It can overfit. It won't have a good predictive power. So what we use are decision tree ensembles or decision tree forests that employ hundreds of different trees and that will ask your input different sets of questions. And then you will take the most common result across all of the trees, and we'll say that that's your final classification. In this case, I had 6 trees, 4 of them classify my sequence as plasmid, so my final classification is plasmid. Okay, so now we need to aggregate the information that comes from both of those branches. So in my network, this is all of those branches are part of a bigger neural network. In my network, the output of the gene-based branch and the sequence-based branch are used as inputs with final branch that I call branch weighting. That will use that will take the output of the gene-based branch, the sequence-based branch, and it has a trainable weight that will weight the contribution of each one of those 2 branches based on the number of genes in the sequence and also how many of those genes were markers. Because if my sequence had lots of markers, I can trust the gene-based branch more. But if my sequence had no marker whatsoever or just one marker, I can put more weight to the sequence-based branch. And at the end of it, what my model will output is the probability of your input sequence being a chromosome, a plasmid, or a virus. In this case, the sequence would be classified as plasmid. Okay. So now I'll explain to you how I trained the model, what the model does, what is its architecture, but how well does it perform? As for now, I've only compared it to one alternative, that is PPR method. As far as I know, that's the only classifier that also proposes to classify sequences into chromosome, plasmids, or viruses. Actually, 2 weeks ago, a new one came out, but it's called Deep Microbe Finder. I tested it and it's really not good. So here I'm only comparing my classifier to PPR meta. I'm calling my classifier here IMGVR classifier because that's how because it will be used to identify sequences for the IMGVR database. Okay, so during training, I prioritize precision over recall. And what does it mean? It means that I wanted to reduce the proportion of false positives. I don't want to classify chromosomes as plasmids or viruses. It's less bad for me to classify a plasmid into a chromosome and just ignore the plasmid than to classify a chromosome into a plasmid or a virus and put that in a database and call that a virus, and the users will think that's a virus. Okay, so in this figure here on the right, I am showing the proportion of sequences that were classified in each of those classes. So my chromosomes. Out of all my chromosomes, 99.2% of them were classified as chromosomes. 0.3 were classified as plasmids, and 0.5 were classified as viruses. So those red crosses below represent the errors, classification errors. For plasmids, I could identify 75% of them. 24% were classified as chromosomes, and 1.5 were classified as viruses. This is kind of expected because plasmids, they don't have a common set of markers that are universal to all the plasmids, and they also have some chromosome-like features. So it was expected that I would not be able to identify a large percentage of them. It is possible to increase the number of plasmids that are detected, but this would increase the false positive rate here, the classification of chromosomes to plasmids, and that's not something that I want. And finally, for viruses, again, I had a low error rate for viruses, and I could classify 96, almost 97% of them correctly. And when we compare this to PPR meta, this other classifier, we can see that this new classifier vastly outperforms PPR meta across all of the different classes. So, bottom line is I'm pretty satisfied. But those results are prone to change because I'm still using lots of markers. 75,000 is a lot, and I will probably need to reduce the total number of markers used for classification. So the numbers here might drop a bit before the final version. Just because for speed concerns, I don't want to take a long time to classify each metagenome. Okay, but there is one footnote. Everything that I described up until now had an assumption that is, the classifier assumes that each given sequence that given as input can only be assigned to one class. So one sequence can either be a chromosome or a virus. But in biology, that's not true because biology is complicated. So lysogenic phages, they can integrate their genome into the host genome using a self-encoded integrase. Integrase is the enzyme that they use to integrate a genome into the host chromosome. And the final result of this process is that now I have a sequence here that is partly host, partly virus. How do I deal with this? So the most common approach to identify those prophages here, prophages are those inserted sequences, is to find islands of viral markers flanked by host-specific genes. But most of our algorithms that are available nowadays, they work well enough, but they can be improved. So what I'm doing is I'm implementing a type of model that is called conditional random field, or CRF. That is a model that uses conditional probabilities to label units of a sequence. For example, genes within a context can be thought of as units of a sequence. And what do I mean by conditional probabilities? It means that the model has a memory, and it can use this memory to make decisions. So let's say that the marker starts from the left here. It will see this host marker, then those two genes that are not host markers, and then it will see a tRNA. Next, it will see a phage marker. Now, what the classifier will do is, well, given that before this gene, this viral marker, I saw multiple host markers and a tRNA, and tRNAs are hotspots of viral integration, this is likely the boundary of the prophage. And then the classifier will continue to analyze the sequence here, and then at one point it will find this host marker. And then what we will do is that, well, given that there is a host marker here and there was a viral specific integrase before, and integrases are also enriched and prophage boundaries. The boundary for this prophage island is around here. So yeah, the model uses this kind of memory, and I say memory in between quotes, to make this sort of classification. I don't have any results to show now because they are very prone to change, but they are very exciting. It seems to be working pretty well. And we are also going then to include prophage identification in IMG. Okay, so up until now, I've been only talking about technical stuff. Gene models and machine learning, but what is pretty cool about all of this is that it will enable us to gain a lot of insights into the ecologies of MGAs. Because viruses and plasmids do not only interact with their hosts, but me in my research project, I'm very interested in understanding how they can interact with each other. Because they share a common host, MGEs, different MGs are subjected for competition for cellular resources, and they're also subjected to genetic exchange between them. And that's what that's my biological research right now. I'll give you guys 2 examples. Again, those are preliminary results. Nothing is final yet, but they're pretty cool, and I really wanted to share them. So while testing the classifier in a couple of metagenomes, I identified some plasmids that possess defense islands containing several antiphage systems. For example, restriction enzymes. Restriction enzymes will cut other viruses when they enter the cell. I also found other types of defense systems, but restriction enzymes are the most common ones. The cool thing is that in the same metagenomes where I found those plasmids, I noticed that the prophages within that are integrated into the bacterial genome are way more likely to encode methyltransferases. And methyltransferases are counter-defense proteins because they will methylate the viral genome, and this will make the viral genome immune to the restriction enzymes. So my hypothesis is that plasmid-encoded defense systems prevent phages that can escape them from integrated into the host genome. So there is a selection pressure here to selecting for viruses that encode those methyltransferases. And when we look at the metagenome, those are the only ones, not the only ones, but those are most of the ones that we see integrated in the genomes that contain those plasmids. So here on the right, I'm showing 2 examples of 2 different plasmids that encode defense islands. And all of those genes in blue are genes from defense islands they form those long stretches of contiguous genes that we call defense islands. Another interesting example that I discovered by accident is that while classifying viruses in a couple of metagenomes, when testing the classifier, I noticed that some viruses, some sequences that I classified as viruses, and they had very viral-like features, like encoding capsid or other structural viral proteins. For some reason, they also encoded plasmid-specific genes. And when I looked at the functions of those genes, most of them had no known function, but some of them encoded proteins of the partition system. The partition system is a set of proteins that stabilizes plasmids during cell division, just to make sure that when the cell is dividing, both of the daughter cells will receive plasmids, and this makes plasmids stable across cell division. So when I took the sequences of those partition proteins from those viruses, and I compared to all of the other sequences in the metagenome. I noticed that those proteins were very similar to other partition proteins that were encoded in plasmids, which is an indicative that maybe those proteins jumped from plasmids to viruses. Just to be sure about that, what I did was I took those plasmids that encoded the partition systems, and I compared them to public virus databases. And I found that the closest relatives to those viruses, they don't encode that partition system, but they do encode an integrase. That is that gene that I mentioned before that the virus or the phage used to integrate into the bacterial chromosome. And integration into the bacterial chromosome is also a strategy and approach for guaranteeing stability across cell divisions, because the virus will be part of the bacterial chromosome, so it will be stable across cell divisions. So my hypothesis is those phage plasmids acquired the partition system via horizontal gene transfer from the plasmid from the same host, and then it lost its integrase. So the integrase is this gene in black in here. So after the virus obtained this partition system from a donor plasmid, it became stable even without the presence of an integrase. As if a plasmid that loses the integrase without having another system to guarantee plasmid stability will become unstable and will be lost after cell division. This is not a new phenomenon. There are a few papers describing things like this, gene sharing between viruses and plasmids. But from what I'm seeing, this kind of interaction between MGs within the same host is way more common than otherwise thought. So yeah, I'm interested now in exploring these interactions between different MGs, either in competition, like with the defense systems, or in gene transfer, like in this example of a virus acquiring genes from a virus acquiring genes from plasmids. So the newly predicted viruses and plasmids will be available in JGI's IMG-VR portal by the second half of 2022. I hope so. And our goal is to allow researchers to explore the diversity, ecology, and evolution of mobile genomic elements using public data that was collected by scientists around the world. And I should mention that we currently do have a database of environmental viruses. It's called IMG-VR, and it's public, and everyone can use it. And what I'm trying to do now is that IMG-VR was developed a couple of years ago when our knowledge about viruses was much more limited. So the current version IMG-VR only identifies some groups of viruses. But still, those viruses are the most common ones, and this is a great resource to explore viral diversity in the wild. The next version will increase the diversity of viruses that are detected and also add plasmids as an additional type of MGs. And that's it. I would like to thank people in my group. Nikos, that is the lead of my group, the microbiome data science group, and my boss. And Stephen and Simon are also scientists at JGI, and they've been helping me with scientific advice since the beginning of this project. And yes, that was it.
Congratulations for your work, for the presentation. Now we have 3 questions by Thiago. When working with genomic data, not necessarily the whole gene sequence is a MGA. It may be inserted in another sequence. Can the model identify and return the coordinates of the inner sequence, and how?
Yes. Let me share my screen again. So I only talked very briefly about this, but this is a very important part of the classifier. So I'm using conditional random fields to identify those MGs that are integrated into the host genome. So this will avoid having the assumption that a given sequence is 100% virus or 100% plasmid or 100% host, because I can identify those hybrid sequences.
The second, no, you can. I think Antonio's back is.
Sorry.
Come back.
Yeah, wrong button.
Hello again.
Not sure if that's answers his question. Does it?
I think it's okay. We have the second one by Rafael. Between environment, soil, ocean, and the abundance of given MGA type.
I can't answer this yet because I still haven't executed a pipeline in all of the metagenomes. I haven't even started. I'm still finishing putting the last touches to the classifier. This should start in January, but from experience, I can say that yes, the environment does influence the MGD content. For example, soils that are very poor in phosphorus, they tend to have less viruses because viruses, they require a proportional larger amount of phosphorus. So even nutrients, the hosts, the species that colonize that environment, all of those factors will influence the MGE content of a given metagenome. For example, in aquatic environments like freshwater or oceans, bacteria and archaea, they move way more freely, so they engage into gene exchange more easily. But I don't have data to support those observations now. I don't think I'm hearing you.
I wasn't. Did you use cross-validation or nested cross-validation in your work to choose parameters?
Yeah, so all of the results that I showed, the performance, classification performance was performed in cross-validation. So what I did was I had, I don't remember now, about 700,000 sequences in my training data. I split that into 5 different folds, and then I used those folds for cross-validation and performance evaluation. One thing that I did, and it was especially useful, was to be sure that I didn't have very similar sequences that were present in different folds. For example, having one strain of one bacteria in one fold and in a different strain of the same species in a different fold, because this will inflate your classification performance, but will not really tell if your classifier can generalize to sequences that are more divergent when compared to the things in your training data. So when doing this cross-validation split, it is important to make sure that the sequences that are very similar are always in the same split. So yeah, the bottom line of the answer is yes, I did cross-validation.
Okay. Thank you again. Congratulations. We have one more question. Did you test another algorithm with random forest?
Oh, okay. I tested lots and lots and lots and lots of algorithms. In the end, I'm not using random forest actually. The tree ensemble that I showed you is not a random forest. It is a gradient boosted tree ensemble. And it's like a random forest is more or less the same thing of having lots of trees doing classification, but the way it is trained is very differently, and it will provide different results. But yeah, what provided me the best results is to have one tree ensemble, in this case, one gradient boost tree ensemble, to classify the features that were derived from gene content, and having another classifier that only use sequence information, and then aggregate those two at the end.
And now the last one. How did you select the parameters of cross-validation?
Yeah, using cross-validation. Again, it was not a random cross-validation. It was a cross-validation that took into account sequence similarity.
So, okay, congratulations. And now we will for lightning talks.
Okay. Well, thank you so much for having me.
Thank you. Thanks so much for your presentation and your work.
Thank you.
Okay. Now we are presentation the lightning talks. The first one is I'm here again. Okay. Now you have two lightning talks. The first one is integration environmental and genomic data through machine learning algorithms for the prediction of stillbirth accessibility in data cattle, which will be presented by Dr. Pablo Augusto de Souza Fonseca from University of Guelph. Thanks, Dr. Pablo, for your participation.
Thank you.
And let's start your video. Right now.
Welcome, my name is Pablo Fonseca and I will present some results about the use of haplotype libraries and machine learning algorithms for the prediction of stillbirth events in Holstein cows. This work was developed at the University of Guelph under the supervision of my advisor, Professor Angela Canovas. Stillbirth is described as the death of the calf just before, during parturition, or within 24 hours of birth. Stillbirth cases are one of the main causes of economic losses in the dairy industry due to the costs associated with the loss of the calf, treatment of dystocia, culling and replacement events, as well as because of the impact over production and also animal welfare. Consequently, understanding the cause of these events is a crucial step for the dairy industry. The main goal of the animal breeding is the prediction of breeding values and or phenotypes using or not genomic data, GBLUP, Bayes alphabet, and models to account for epistatic dominance and codominance are common approach to estimate the genetic values of the individuals. However, machine learning have increased in popularity in the livestock sector due to some characteristics such as non-parametric and flexible behavior, the ability to learn from the data, consequently allowing the identification of hidden patterns, and the ability to deal with the curse of dimensionality. Additionally, in deep neural networks, for example, the predictions tend to be based on the overall genetic relatedness rather than on the effects of particular markers. Consequently, machine learning algorithms are good alternatives for the genomic analysis in the livestock sector. The main objective of this study was to evaluate the prediction accuracy of different supervised machine learning algorithms in different scenarios regarding stillbirth events. First, predicting each individual regular birth and stillbirth event, and subsequently predicting cows with higher risk to have a stillbirth event, which were previously classified in high and low risk groups using a threshold model. Additionally, the number of scenarios was expanded, including different combinations of features composed by haplotype libraries and environmental information. Initially, the haplotype libraries used in the prediction were obtained from previous work of our research group, where a haplotype-based GWAS for stillbirth was applied using a repeated measure model, and in this study we used more than 50,000 pregnancy outcomes and around 13K pseudo-SNPs, which were included in the model to identify genomic regions associated with stillbirth events. And the following variables were included in the model, which you can see in this slide. From these GWAS, around 500 pseudo-SNPs were significantly associated with the number of stillbirth events after a false discovery ratio adjustment of 5%, and composed the haplotype libraries included as featured in the predictions. All these pseudo-SNPs were mapped in autosomal chromosomes. And it's important to highlight that this study was recently accepted for publication in Journal of Dairy Science and is currently in press. Two initial predictive scenarios were designed. First, each individual birth record was predicted, and second, classification of cows in high and low risk groups was performed. Initially, the cows were classified using two threshold models. The first one, cows with the number of stillbirth events higher than the quantile 75, were classified as high-risk cows, and in the second threshold, cows with a number of stillbirth events higher than the quantile 90% were classified as high-risk cows. Subsequently, the number of predictive scenarios was expanded, including different combinations of features. In total, 5 predictive scenarios were created. In the still scenario, where each individual birth record was predicted, 3 combinations were created. First, all features, haplotype libraries plus environmental features were used in the prediction. Second, only the haplotype libraries were included in the feature list. And 30, only environmental features were used. In the threshold classification scenarios, only haplotype libraries were used for the prediction. Regarding the predictions using machine learning algorithms, initially the datasets were split in trained and test sets, with 70% and 30% of the original datasets respectively. For the predictions, 2 linear models and 5 machine learning models were used. The linear models were included as a baseline to compare the machine learning algorithms in relation to linear models. Consequently, together, the number of initial predictive scenarios and models resulted in 35 predictive scenarios. The best trained model in each algorithm was applied in the test dataset. And finally, the test model performance on the test dataset was evaluated based on accuracy, balanced accuracy, error under the curve, residual mean square error, precision, recall, and F1 metrics. When the accuracy in black bars and balanced accuracy in blue bars in the plots were compared, it's clear to notice a substantial difference between those metrics, with a trend of accuracy show higher values. Usually, the number of stillbirths is substantially smaller than the number of regular births, consequently resulting in unbalanced datasets, which can explain these results. The largest balanced accuracy was obtained for the threshold model using the 75% quantile classification and in the still all scenario. In both cases, the extreme gradient boosting outperformed other machine learning algorithms. And when additional performance metrics were evaluated, less stringent quantile classification resulted in a better performance for the predictions, as we can see here in the red bars in the plot. Interestingly, the extreme gradient boost resulted in higher balanced accuracy, area under the curve, F1, recall, and lower residual mean square errors. In the scenarios including the individual birth records, the combination of haplotypes and environmental features resulted in the best predictive performance, with the extreme gradient boosting outperforming other machine learning algorithms, showing higher balanced accuracy, area under the curve, F1, and recall. Another important characteristic in the predictions used in machine learning algorithms is the computational time during the hyperparameter tuning stage. The CPU system time for the extreme gradient boosting showed it to be the largest one, with around 55 hours in the worst scenario. However, when the real-time wall clock time is compared among the algorithms, the MLP wave decay ML and Randolph forest have substantially larger computational times. The future contribution for the accuracy improvement was evaluated in the best predictive scenarios, still all in quantile 75, as shown in these slides. It's interesting to highlight that when the two best predictive scenarios are compared, the improvement in accuracy caused by each pseudo-SNP is similar. For example, despite the absence of environmental feature in the quantile 75 scenario, which were the main responsible for the improvement in accuracy, the still all scenario, the final balanced accuracies are very similar. Consequently, suggesting a large and more homogeneous contribution of the feature's importance across the pseudo-SNPs. This is reinforced when the means for the improvement in accuracy are compared between the still all and quantile 75 scenarios, considering only pseudo-SNP's contribution. The leading contribution of environmental features for the improvement in accuracy in the still all scenario are supported by the low readability and large contribution of environmental components for the stillbirth in the Riquero. Here, the largest contribution for the increment in accuracy was observed for first call age class, calls younger than 36 months, followed by early year season and the size of the calf. All these components were previously evaluated in the literature regarding stillbirth and reinforce the results obtained here. And due to the black box nature of several machine learning algorithms, it's difficult to extract relevant biological information from the feature's contribution. However, when you analyze the enrichment status for quantitative trait loci annotated within genomic coordinates of the top 100 pseudo-SNPs contributing for the majority of the accuracy improvement in the best predictive scenarios, some interesting results were obtained. Several reproduction-related key tails were enriched in those regions, with interval from first to last insemination and gestation length the most enriched key tails in the still all and quantile 75 scenarios respectively. Additionally, in some of the haplotype blocks harboring pseudo-SNPs, which contribute with the largest proportion of the accuracy improvement in the best predictive scenarios, functional candidate genes could be annotated. For example, in the block 59 on BTA9, which was responsible for the largest increment in accuracy, we could annotate the gene GRM1, which encodes the protein mGLUR1, and mGLUR1 has a protective potential against periventricular leukomalacia in premature infants, a common abnormality found in brains of stillborns. However, in some cases, it's difficult to understand the biological meaning behind the result. For example, in the haplotype block 50 on BTA11, which was responsible for the largest accuracy in the increment of accuracy in the still all scenario, we don't have any gene close and any indication of some regulatory element. It's interesting to highlight that the predictive performance obtained here is higher or similar with other performances obtained in other studies, using genetic markers or environmental information, as we can see in this slide. In conclusion, the use of haplotype libraries and machine learning algorithms showed to be an interesting alternative for the prediction of stillbirth in the Riquero. In addition, an important contribution of environmental features was observed during the prediction of stillbirth events. In the threshold model, less stringent thresholds result in better predictive performance. Regarding different machine learning algorithms, extreme gradient boosting algorithm outperformed other predictive models in the best scenarios, and it's interesting to highlight that relatively high balanced accuracy were obtained using the extreme gradient boosting in an unbalanced dataset, which results in trained models that are closely related to real-world scenarios. And finally, regarding haplotype libraries using for prediction, the further investigation of these genomic regions might help to better understand the genetic architecture of stillbirth in host and cattle. I would like to thank you for the attention of all the funding agents and the Canovas lab team at the University of Guelph to help in the development of this work. Thank you very much.
We have one question about your work. How did you set up the train test validation set? You are muted.
I was muted. So yeah, basically what we did was split our data set in 70% in training data set, 30% in test data set, using an equal proportion of stillbirth and regular births. As I mentioned, we have a substantially smaller number of stillbirths, what is good because we don't expect a lot of gestation loss in the dairy population. So we try to keep it balanced, the proportion, the ratios between regular and stillbirth events, but splitting 70% for training, 30% for test set.
Did you use cross validation?
Yes, we use for all the models when possible 5-fold cross validation.
Okay. We don't have more questions. Thank you.
You are
Congratulations.
Thank you very much.
Now, we have the second lightning talk. That is cell segmentation for range spatial resolution through morphology analysis, which will be presented by Rafael dos Santos, which is an undergraduate student from Universidade Federal de Santa Catarina. So, I will start the video. Right.
Hello everyone, my name is Rafael dos Santos Peixoto. I'm a control and automation engineering student at the Federal University of Santa Catarina, and I'm also an undergraduate researcher at Lammert's da Rocha Lab, collaborating with the DRICE Lab from Boston University. Today, I'll explain our method that uses cell segmentation for enhancing spatial resolution through morphology analysis. So first, I'll give an introduction about the field of spatial transcriptomics. I'll say the objectives of this project, the methodology, the results, and finally a conclusion. To get started, in 2013, the Nature magazine defined single-cell RNA sequencing as the method of the year because of the breakthrough this technology represented and how we understand tissue diversity. Later, in 2020, the same magazine defined spatially resolved transcriptomics as the method of the year because this technology not only enabled the single-cell resolution in some cases, but also the spatial information of the tissue, of the cell. So, current methods for spatial transcriptomics can be divided in two major categories, the subcellular and the spot-based ones. In the subcellular, that is presented in this slide from the Marefish data from the Vision company, they obtain this data by taking multiple pictures of fluorescent molecules that attaches themselves to the transcript, and they merge these pictures together. But the limitation of this technology is that it can only capture a limited amount of transcripts at a time, so around 500. And the other technology, the spot-based one, attaches barcodes to the tissue and then sequence the transcripts, and from the associated barcode they know where the transcript came from. The problem with this technology is that the barcodes measure 55 micrometers wide. And because of this, they can contain more than one cells, usually from 5 to 10, and they do not have a cellular resolution. To overcome these challenges, some scientists designed methods for cell type deconvolution, where you have like a spot with multiple cells, and then you can know the percentage of types in that spot. To give like to make you understand our major objectives in this program, in this project, I'll explain step by step about what we're going to do. So here in this image, you can see the tissue, and you can see also circles representing these spots. And as you realize, there are more than one cell in each spot. Applying the convolution method, we can obtain the percentage of type inside that spot. So in this illustrative case, we have half of the cells from cell type 1, we have like 1/4 from cell type 2, and also 1/4 from cell type 3. The problem is that we can only get the percentage, but we do not know which cell is from which type. And motivated by this reason is that we are looking to enhance the resolution of spatial transcriptomics by assigning the cell type to the specific cell location. Because of that, we need to know where the cells are located. And to do so, we are using cell segmentation. This is the first step on our project, and this will be the step I'm explaining today. And from the segmented cell, we can also extract morphology information, that is the cell shape, the cell size, and then we aim to apply a classification algorithm to assign the cell type to the specific location. So here you see that most of the cells are from type 1 and the other ones are from type 2 and 3. In summary, the objective of this project is to enhance the resolution of spatial transcriptomics by assigning the cell type to the specific cell location. And to do so, the first step is to segment the tissue, the cells in the tissue, then assign the cell type, and finally we need to validate this code. And since we cannot validate on the spatial transcriptomics, we'll be using the Marefish data as it has subcellular resolution. And whenever you have spatial transcriptomics data, you get an H&E image associated with the expression matrix. And this H&E image is a combination of two stains, amatoxylin and eosin. The amatoxylin represents the nuclei, and it's on the purple color, and the eosin represents the extracellular matrix and the cytoplasm in pink. So in this case, we'll be focusing on the purple color that represents the nuclei. But as I mentioned, we cannot validate this data on the spatial transcriptomics dataset. We'll be validating on the Marefish dataset that presents another staining. It presents a DAPI image. And in this case, we also have a fluorescent staining that attaches itself to the regions on the DNA. And we also have the information about the nuclei of the cells. So first, we are creating pseudo-spatial transcriptomics from this DAPI image, and we are assigning the expression information from each cell to the barcoded it's located around that cell. So the methodology here that we'll be focusing now is how to segment the cells from the tissue images. And there are many methods to do so. We have tried a couple of them. And in the first part, we tested unsupervised methods. In this case, we do not need to have the annotations about the cells. We only need to test a few parameters. So first, a simple threshold that will segment the regions in two parts if they are above a certain level of color or a certain level of brightness. And in this case, you can see that the cells are not segmented correctly, because when the regions, when they are close to each other, the algorithm assigns them to the same space. So we tried another method, which is blob detection, that tries to detect circles around the image. But since some cells have different shapes, it didn't work very well either. And you can also see that we tried to equalize the contrast of the image and bring more brightness to the cells, but that also didn't help solving the problem. So we tried another algorithm that's called k-means, that tries to divide the colors in groups depending of the parameter k that's specified for the algorithm. And with the same problem of the threshold, it joined the cells that were close together into a single place. On another, by using these methods, we can also see that some of them work well when the cells are away from each other, but when the cells are together, they fail. So we tried another method that's called local threshold, and differently from the first threshold method, it does not use the same value for all the places of the image. Instead, it measures what will be the best threshold for that specific region of the image and segmented that region according to this value. So on the right side, you can see that this result is a lot better than the other ones. And with some refining, for example, removing the white lines, removing the noise, we can have good results of the cell segmentation. Another approach is to try supervised methods that use neural networks, but in this case, you need the information of where the cells are to train an algorithm that will predict the cell location. As we did not have enough resources to label all the cells, we tried some methods that are available in literature. The first of them is CellPose, which is a generalist algorithm for cellular segmentation. And it segmented well for some parts, but not very well for others. And this can be because the data that they trained the model is different from the data we are using now, or maybe the parameters. So in the left case, we see like when you set the parameter of the cell diameter to 50 microns to 50 pixels, and when we set to 60 pixels on the right, and we got different results. So that's another important aspect to look at. We also tried Stardist. It worked well at first, but whenever you get to these more dense locations, it fails. We also tried semi-supervised methods such as Weka, in which you can label some cells, and then the algorithm will predict for the other cells. And in this case, it also failed for that region when we have multiple cells. But finally, we got a good result with the Mesmer algorithm. It was specifically trained for dap-stained images, so that's why it worked well on our data. And we'll be using this algorithm on the rest of our pipeline to then extract the morphology information and classify the cell type. So in conclusion, the local threshold was able to handle the difference between densities on the image, and that's why it was the only unsupervised method that performed best. And also, except for the Mesmer algorithm, the other supervised methods did not perform properly because of the difference between testing and training. And also, to apply this information to the AGNE image, we only need to segment the purple channel that has the nuclei information. So here are the reference used in this presentation, and here is my contact information. Thank you very much.
You are muted.
Okay.
Congratulations for your work. I have two questions here. Which database of image did you use?
We use the database that is provided on the company website. So for the DAPI image, that's like the black one with the white spots, they provide it on the website of the VisGen company. And for the other image, the AGNE image, our lab acquired some data, and we were testing on that data.
Okay. The second one, what are the main morphological characteristics you use it for training your algorithms?
We're still not sure about the main morphological features, but we'll probably be using the major and minor axes, the shape, so things like that.
I will ask another one. How did you set up the train test validation? Did you use cross validation with folds?
Oh no, in fact, we did not
In
have,
Medi, we
we didn't, we did not use label data, so we did not validate if the segmentation was properly working. Instead, we used the algorithm that's called Mesmer, which was trained and validated before and was available publicly as like R-based. And also the company which provides the data also provides the label. So we could use that to check if our validation is working fine.
Okay. Thank you.
Thank you
Congratulations
very
again.
much.
So now we have your last presentation, but this presentation will be in Portuguese. So we come back at 4 p.m. to the last presentation with Dr. Karina in Portuguese. So see you. Oi, gente, estamos de volta. Como a última palestra é em português, então eu vou fazer a apresentação dela também em português. A doutora Karina de Santos Machado é engenheira de computação pela Universidade Federal do Rio Grande. Oi, Karina. Você está mutada.
Olá,
Tudo bem?
tudo bem.
Atualmente é professora associada da Universidade Federal do Rio Grande, onde coordena o grupo de pesquisa e laboratório de biologia computacional. A palestra da Karina vai ser aprendizado de máquina aplicado a docking molecular e triagem virtual. Só dar um comentário que as perguntas também podem ser feitas em português pelo chat. E é isso, é com você, Karina.
Então tá, obrigada, Tayana, pela apresentação. Eu estou ouvindo agora sim. Então tá, pessoal, vou colocar em tela cheia. E aí qualquer coisa, Tayana, tu me avisa que eu não vou estar enxergando vocês. Então, pessoal, primeiro, I would like to apologize, but I'm going to talk in Portuguese. Eu decidi fazer a palestra em português porque eu acho que a nossa comunicação, a nossa troca, ela vai se dar melhor em português. Mas eu fiz os slides em inglês, então, if someone wants to this presentation in English, I can send this by email after presentation. E se alguém quiser ela também, igual em português, eu posso mandar depois os slides, tá? Porque tem bastante referências, eu acho que vocês vão poder aproveitar. Então, o que nós vamos conversar hoje é sobre aprendizado de máquina aplicado a docking molecular e triagem virtual. Então, gostaria de iniciar agradecendo o convite, né, da Gisele, da Tayana, para estar aqui hoje com vocês. Eu acho que foi um dia que nós podemos compartilhar muita informação interessante, né, vários trabalhos muito legais. Eu não conhecia a maioria dos colegas que apresentaram. Acho que foi um evento muito importante, né, para trazer a aprendizado de máquina para a bioinformática. E também gostaria de agradecer quem está assistindo, né, num sábado, participando de um evento. É bem legal, assim, fico bem feliz. Então, vou iniciar me apresentando, tá? Eu sou professora hoje na Universidade Federal do Rio Grande. Eu sou formada em engenharia de computação, com mestrado e doutorado em computação. E junto com o professor Adriano, a gente coordena o grupo de biologia computacional aqui na FURG. Onde que eu estou, tá? Eu gosto sempre de falar, assim, porque é bem comum. Quem não conhece a universidade acaba, às vezes, confundindo com a Universidade Federal do Rio Grande do Sul, que fica em Porto Alegre. Tá? Nós estamos na FURG, que é a Universidade Federal do Rio Grande. A gente fica na cidade de Rio Grande, aqui no sul do Rio Grande do Sul, para quem não conhece. Tá? Então, aqui eu coloquei umas fotinhas da cidade, uma cidade com praia. E aqui tem o site da universidade, então quem quiser conhecer um pouco mais da universidade, depois também pode visitar o site. Na FURG, eu estou alocada dentro do Centro de Ciências Computacionais, tá? Onde eu oriento alunos de pós-graduação na computação e também nas ciências da saúde, mestrado e doutorado, tá? Então, eu tenho um trabalho bem interdisciplinar mesmo, a gente tem alunos tanto na área de computação, quanto a gente hoje orienta alunos da enfermagem, fisioterapeuta, todo mundo trabalhando com bioinformática, biólogo, bioquímico. Esse é o nosso grupo, tá? O Combilab. Aqui está a página do Git do grupo, que a gente está começando a colocar conteúdo nessa página. O nosso grupo ele existe desde 2012, mais ou menos. A gente tem trabalhado principalmente com bioinformática estrutural e dentro de bioinformática estrutural, com docking molecular, dinâmica molecular e modelagem molecular. Em docking, eu trabalho desde 2005, desde o meu mestrado, eu trabalho nessa área de docking. Então, por isso que depois que as gurias convidaram para participar do evento, eu achei que poderia contribuir no evento trazendo aplicações de aprendizado de máquina nesse contexto de docking e triagem virtual. Então, como eu não conhecia muito o público que estaria aqui hoje, eu vou falar muito rapidamente, né, sobre alguns conceitos dentro dessa área de pesquisa de docking molecular, triagem virtual, para depois a gente conseguir entender as aplicações de machine learning nesse contexto. Então, assim, né, ferramentas computacionais, elas têm sido desenvolvidas e utilizadas na descoberta de novos fármacos, né, há muito tempo, né, como uma alternativa para os experimentos tradicionais. Por que se usa a computação, né, dentro desse processo de descoberta de um novo fármaco? Para reduzir o tempo, porque esse processo geralmente é muito longo, e também, principalmente, reduzir os custos envolvidos. Então, a identificação de novos hits, né, de novos candidatos promissores a novas drogas em grandes bibliotecas, por modelos computacionais, tem sido alvo de estudo da indústria farmacêutica. E reduzir esses custos associados a esse tipo de experimento tem sido o objeto de estudo de muitos indústria e também na academia. Em paralelo a isso, a gente tem um crescimento, né, de experimentos de high throughput screening que estão gerando enormes quantidades de dados. Então, a gente tem nessa área dados que a gente pode até classificar como big data, né? Então, para conseguir usar essa enorme quantidade de dados que estão sendo gerados não só por high throughput screening, mas também por dados experimentais, né, de estrutura de proteínas, enfim, para a gente conseguir usar esses dados de forma efetiva para contribuir na busca de novos fármacos, a gente tem que aplicar técnicas computacionais baseadas em inteligência artificial. Então, aí que vem, né, essa relação do aprendizado de máquina com triagem virtual e doc molecular. Mas, para quem não conhece, o que seria triagem virtual? Então, a triagem virtual, ela são técnicas computacionais que a gente utiliza, né, que permitem aos químicos, aos farmacêuticos, aos pesquisadores em geral.
Karina?
Oi.
Não sei se você está passando os slides, eles não estão no modo apresentação, daí não está passando.
Eu estou passando. Poxa,
agora funcionou. Acho que, não sei se tinha travado.
Vamos ver. Deve ter travado. E agora?
É que quando você coloca no modo apresentação, não aparece pra gente. Eu acho que você tem que compartilhar de novo.
Deixa eu compartilhar a tela, então, peraí.
Tá bom.
A tela toda, só um pouquinho. Vamos ver. Eu vou só parar e vou compartilhar a tela. Eu não sabia que não estava, vamos ver. Eu já fiz outras vezes com essa ferramenta e deu certo.
Eu acho que tem que ser a tela inteira mesmo.
Tá. E assim?
Tenta passar? Agora tá funcionando. Beleza.
Tá funcionando? Então tá. Bom, então não perdemos muito de slides, assim, só vocês não viram onde fica Rio Grande. Então, pessoal, o que seria a triagem virtual? Então, utilizar técnicas computacionais para reduzir enormes bibliotecas virtuais de moléculas, né, para um tamanho possível de a gente testar tanto em sílico, depois nas próximas etapas in vitro e in vivo. Então, a triagem virtual ela é amplamente utilizada como um guia no desenho racional de fármacos, que é esse desenho de fármacos como uma etapa computacional. Então, aqui nessa figura, vocês podem ver aqui os principais bases de dados de moléculas, né, de acesso gratuito. Tem mais, mas as que a gente utiliza hoje, principalmente no nosso grupo, são essas. A gente tem o Zinc, o Drug Bank e o PubChem. E aí a gente tem esse filtro que ele pode já utilizar técnicas de machine learning nesse filtro, né, para então reduzir essa quantidade de moléculas para serem testadas nas próximas etapas. Então, o que é desenho racional de fármacos? Então, o desenho racional de fármacos é esse processo que utiliza uma etapa em computador para acelerar e reduzir os custos no desenho de um novo medicamento. Esse processo foi proposto por Kuntz em 92, nesse artigo, e ele diz, né, que esse processo é composto principalmente por essas etapas, onde a gente começa selecionando o alvo, que é a estrutura do receptor. Conhecendo a estrutura do receptor, a gente seleciona um conjunto de candidatos a inibidores, que são os ligantes, e aí a gente avalia a interação dos receptores e do ligante com algoritmos de dock molecular. Baseado nessa análise de interação, os ligantes que têm melhor resultado em sílico, a gente passa para as próximas etapas, né, do desenho de um novo fármaco, sintetizar e testar experimentalmente. E aí, se esses resultados experimentais forem promissores, se vai para as próximas etapas, se não, se volta, se seleciona um novo subconjunto. Geralmente, essa seleção de subconjuntos é feita com triagem virtual, onde eu já posso usar, né, machine learning ou não. E essa avaliação da interação entre o receptor e o ligante, ela é feita, então, com docking molecular. Então, para quem nunca viu, né, um processo de docking, aqui a gente tem uma proteína-alvo e um candidato a inibidor, nesse caso era um nanotube de carbono. Então, o docking ele é um método para avaliar a melhor conformação e orientação de uma molécula no sítio de ligação de uma proteína-alvo. Então, o docking ele vai buscar uma abordagem, né, para tentar caracterizar o comportamento dessa interação de um ponto de vista, né, também de um processo bioquímico. O programa de docking ele envolve principalmente, né, duas características, duas partes, tá? Uma que vai tentar encontrar a melhor conformação e orientação do ligante, que é a etapa de busca, o searching, e uma função que vai avaliar a qualidade, entre aspas, tá, dessa interação, que é o score, né, energia livre de ligação, que é estimada porque a gente não consegue computacionalmente ter exatamente o valor experimental, então é um valor de energia estimado. Então, nesse processo todo, tanto na triagem virtual, no desenho racional de fármacos e no docking, a gente pode aplicar aprendizado de máquina em diferentes momentos e para diferentes objetivos. E o que eu vou tentar agora apresentar a vocês é algumas possibilidades de aplicação de machine learning nesse contexto. Então, a gente vai começar com uma visão bem macro, uma big picture de onde eu posso usar machine learning em triagem virtual e desenho racional de fármacos. Depois eu vou, então, refinando até chegar em como a gente está utilizando hoje no laboratório, em 2 trabalhos que a gente fez nesse contexto. Então, de uma visão bem geral, essa revisão aqui, dessa referência, eles usaram machine learning para... fizeram uma revisão sobre machine learning aplicado à descoberta de novos fármacos e desenvolvimento de novos fármacos, de uma visão bem ampla. Então, aqui, já para a gente começar também a conversar sobre que tipo de técnica de aprendizado de máquina e de algoritmo aparece com mais frequência nesse contexto, nessa área de pesquisa. Então, a gente pode ver que nessa big picture, né, de desenho de fármacos, a gente tem, nessa revisão, né, ele mostra métodos de regressão sendo usados, diferentes métodos de regressão, diferentes métodos de classificação, como SVM, redes neurais, nearest neighborhood, diferentes métodos de agrupamento, como caminhos, métodos hierárquicos e outros, sendo usados em várias etapas relacionadas a várias atividades no processo de descoberta de um novo fármaco. Eu destaquei alguns aqui que têm a ver com o desenho racional de fármacos, assim, um pouco mais específicos. Então, por exemplo, no virtual screening, na identificação, na predição da sensitivity do fármaco que tu está avaliando, em modelos QSAR ou QSAR, na predição da drogabilidade de uma determinada interação proteína-ligante. Então, aqui é uma visão geral, vocês podem ver que muitas técnicas são usadas para diferentes etapas nesse processo complexo de desenho de um novo fármaco. Especificando um pouco mais, né, aprendizado de máquina em triagem virtual, aí em uma outra revisão de outros autores, a gente tem aqui o processo de triagem virtual, que, segundo esses autores, pode ser baseado no ligante ou baseado no alvo, né, na tua proteína-alvo. Tu poderias aplicar o aprendizado de máquina para fazer, por exemplo, a relação, né, QSAR, a gente poderia fazer, aplicar machine learning para fazer a modelagem do farmacofórica, da interação, da região de ligação dessa tua proteína-alvo, para selecionar candidatos a inibidor baseado em similaridade, aplicado em algumas etapas do docking. Então, a gente tem aqui em diferentes momentos da triagem virtual, a gente também pode aplicar machine learning. Então, uma das áreas, digamos, que se usa machine learning nesse contexto há mais tempo é o QSAR. Então, o QSAR, para quem não conhece, tá, é Quantitative Structure Activity Relationship. Ele tem por objetivo modelar, encontrar relação entre estrutura química e atividade de um fármaco, estrutura química com atividade. Esses modelos preditivos dessa relação, eles envolvem, geralmente, a identificação de compostos que são mais promissores, esses chamados compostos HIT, que podem, então, ser sintetizados e vão seguir nas próximas etapas do desenho de um novo fármaco. Então, o objetivo principal desse tipo de modelo, que usa machine learning, né, é otimizar, geralmente, né, otimizar compostos que já existem com algumas modificações de forma a melhorar a sua atividade. Tá? Esses modelos, que é SAR, eles podem ser feitos baseados em estruturas, informações 1D, 2D, 3D do teu ligante e da tua interação proteína-ligante. Então, aqui fica mais fácil da gente ver. Então, esses modelos, eles usam a machine learning, né, algoritmos preditivos, para tentar relacionar atributos como, quando a gente está falando de 1D, tipos de átomos, número de átomos, ou 2D, número de ligações rotacionáveis e outras informações sobre a molécula, ou 3D, por exemplo, área acessível ao solvente, o volume de Van der Waals ocupado, né, por essa molécula. Então, relacionar esse tipo de descritor com a atividade. Quando eu encontrei essa relação e eu tenho uma nova molécula, eu posso, então, predizer para essa nova molécula qual seria, dadas as características, né, os descritores dessa nova molécula, qual seria a atividade dela dentro daquele contexto que tu fizesse o teu modelo. Então, aqui é uma aplicação, né, de machine learning dentro desse contexto de RDD, virtual screening, né, com os modelos QSAR. E aí a gente tem muitos trabalhos de revisão, que eu vou deixar aqui na apresentação vários dessas revisões, porque eu creio que a revisão, trabalhos, né, artigos de revisão, são um bom ponto de partida para quem quer começar a trabalhar com machine learning num contexto de virtual screening ou de docking. Então, tem revisões para vários tópicos nesse contexto, né? Então, a gente tem dessas revisões, que depois eu posso mandar essa apresentação para vocês, eu destaco algumas tabelas dessas revisões para a gente já ir discutindo sobre que técnicas e algoritmos se fala mais, né, e para que eles são usados. Então, nessa tabela, a gente pode ver alguns algoritmos que são usados, né, dentro desse contexto. Então, a gente tem algoritmos, por exemplo, SVM, Random Forest, que é um algoritmo bastante, né, comum, Linear Regression, Naive Bayes, KNN, Gaussian Process. Então, vários algoritmos diferentes sendo usados para, principalmente, modelos QSAR, funções de score para docking, filtro de datasets, filtro de ligantes baseados em similaridade. A gente tem aqui uma outra tabela específica para docking, também de um artigo de review, onde a gente tem algoritmos de machine learning sendo utilizados, né, aqui, algumas funções de score, principalmente para desenvolver novas funções de score baseadas em machine learning ou para triagem virtual, como a gente pode ver aqui no uso. Então a gente chega no machine learning para dock molecular. Então a gente tem essa big picture, né, para triagem virtual, modelos QSAR, filtro de ligantes, enfim, e agora especificamente dentro do docking molecular. Para que a gente onde a gente pode usar machine learning? É claro, né, que não está restrito ao que eu estou falando aqui. Eu estou fazendo uma figura, uma fotografia, né, dessas aplicações. Existem muito mais do que eu estou falando aqui. Então, para quem não conhece, né, o docking, resumidamente, as principais etapas de docking envolvem essas seguintes etapas aqui, né? Claro que vai variar um pouco de acordo com a ferramenta de docking que tu utiliza, mas, em geral, a gente poderia resumir o docking com essas seguintes etapas. Obter a estrutura do ligante e do receptor, preparar o receptor e o ligante, definir a caixa, o sítio, onde tu vai fazer o docking, executar o docking e analisar os resultados. Quando a gente está falando de obter a estrutura do receptor e do ligante, para fazer esse docking, a gente vai obter essa estrutura. Pode obter, né, de bancos de dados onde essa estrutura já está lá, ou eu posso precisar modelar essa estrutura. Quando eu preciso modelar a estrutura, a gente tem aqui uma das principais aplicações de machine learning que foram desenvolvidas dentro da história do uso de inteligência artificial, né, que é o AlphaFold. Vocês devem ter ouvido falar, já conhecem, né, que é esse algoritmo baseado em Deep Learning, né, para a modelagem de estrutura de proteínas. Então, já na obtenção do teu alvo para fazer docking, tu já pode estar usando Machine Learning, que é para tu obter a estrutura do teu alvo. Esses outros modelos, outras ferramentas que eu coloquei aqui, o PyTester, Fire2, o Modeler, eles podem ou não ter etapas, né, de aprendizado de máquina para alguma etapa de refinamento das estruturas, mas o AlphaFold eu destacaria por ele ser baseado em Deep Learning, né? Então, além de ter a estrutura do meu alvo, eu preciso da estrutura das minhas moléculas, e essas moléculas, então, eu posso obtê-las desses bancos de dados públicos, né? A gente cita 3 aqui, o Zinc, Drug Bank e PubChem, onde aqui eu posso já precisar usar algoritmos de machine learning para reduzir e ter uma quantidade menor de moléculas para a etapa de fato, fazer o docking molecular. Aí depois, então, que eu já tenho as estruturas, eu vou, então, preparar essas estruturas do receptor e do ligante para fazer o meu docking molecular. Quando eu vou preparar as estruturas, em condições ideais, no mundo real, digamos assim, não no simulado, né? As proteínas, elas não são rígidas no ambiente celular, elas são flexíveis. E a flexibilidade das moléculas, ela se reflete através de vibrações, de ligações, de ângulos, de diedros, enfim. E essa é uma característica, a flexibilidade das moléculas, que deveria, né, ser incorporada no docking molecular. Só que o ligante flexível, a maioria dos softwares de docking já considera, porque é uma molécula com poucos graus de liberdade. A gente tem, sei lá, 100 átomos que tu pode ter, né, alguns ângulos de rotação, enfim. Agora, quando a gente fala isso é o ligante, né? Quando a gente fala da proteína, ainda é um grande desafio na área de docking, um desafio ainda em aberto, que é incorporar a flexibilidade do receptor no experimento de docking. Para a gente fazer isso, existem muitas técnicas, eu estudei isso no doutorado, daí no pós-doutorado, que eu estive na França, eu voltei a estudar esse assunto. Existem muitas formas de fazer isso, que pode ser baseado em uma estrutura do receptor, e aí aqui tem alguns exemplos de trabalhos que fazem isso, mas podem ser baseadas em múltiplas estruturas do receptor. Quando eu quero incorporar a flexibilidade do receptor no docking a partir de múltiplas estruturas do receptor, eu provavelmente vou precisar usar machine learning para reduzir esse escopo um pouco, né? E conseguir fazer essa incorporação da flexibilidade. Então, eu posso gerar múltiplas estruturas, por exemplo, com dinâmica molecular, e encontrar as estruturas mais representativas por meio de algoritmos de agrupamento. Então, aqui nesse caso, nesse contexto de incorporar flexibilidade por meio de múltiplas estruturas, eu usaria agrupamento, né, como técnica de machine learning no docking. Ou eu poderia usar análise do componente principal, aplicar machine learning a partir de dados relacionados a distâncias interatômicas entre proteína e ligante, dentro só da proteína, enfim. Aqui, então, já tenho várias técnicas de machine learning que eu poderia usar nesse contexto. Ainda nos passos do docking, a seguir que eu já obtive as estruturas, preparei, né, ligante e proteína receptor, considerando a flexibilidade ou não, eu vou precisar definir a caixa de simulação. Então, o grid box é essa região, né, que o algoritmo de docking vai ficar, então, buscando a melhor conformação, orientação do ligante. Essa caixa de simulação, a gente pode fazer ela de forma blind, onde eu vou fazer uma super caixa em torno de toda a estrutura da proteína, mas isso torna o meu experimento um pouco menos preciso. Mas eu posso, então, se eu não sei onde é o sítio, né? Se eu sei, eu desenho já a caixa em torno do sítio, enfim, está resolvido o problema. Se eu não sei o sítio, ou eu faço blind, ou eu tento usar algum preditor de sítio. E aí aqui tem muito algoritmo de machine learning também sendo usado para predição do sítio de ligação da proteína. Então, eu tenho esse artigo também de review aqui, que ele descreve uma série de ferramentas baseadas em machine learning, e aqui específicas baseadas em deep learning, só para predizer o sítio de ligação de proteínas quando a gente não conhece o sítio. Então, aqui a gente tem, por exemplo, muitos baseados em SVM, baseados em random forest, regression. Aí vocês podem ter uma ideia também dos algoritmos, né? Alguns baseados em agrupamento, por exemplo, aqui baseado no caminhos, e alguns aqui, então, usando deep learning para fazer essa predição do sítio. Então, mais uma vez, né, mais uma possível uso de machine learning dentro do contexto de docking. E por fim, né, eu vou agora, que eu já defini o sítio, usando machine learning ou não, né, se eu não conheço, eu posso usar, eu vou executar o meu docking. Então, aqui que eu gostaria de aprofundar um pouco dentro da execução do docking, a gente tem uma etapa de busca, que pode ser usando diferentes algoritmos, vai depender da ferramenta de docking, e para cada posição que tu está buscando, né, que o algoritmo de docking está buscando, a gente então faz a predição desse score usando uma função de score. Essa função de score, ela pode ser de vários tipos, mas ultimamente, nos últimos anos, tem aparecido muitas funções de score baseadas em machine learning. E é aqui que eu gostaria de aprofundar um pouco nessa conversa com vocês. Então, as funções de score, elas podem ser baseadas em campo de força ou physics-based, né? Alguns autores classificam como physics-based, que é aquela que soma todas as interações intermoleculares entre átomos, né? Utilizando algum determinado campo de força. A gente tem as funções de score que são empíricas, onde a gente não vai considerar todos os parâmetros envolvidos nesse processo, né? Mas alguns deles, alguns vão estar pré-calculados, outros são calculados à medida que a função é executada. Funções de score baseada em conhecimento, que vão usar algumas observações estatísticas, né, e pré-calcular. E aí a gente tem as funções de score baseadas em machine learning. Então, como a gente pode usar aprendizado de máquina para desenvolver uma função de score para o docking proteína ligante? Então, a gente teve aqui na FURG um trabalho, uma dissertação, na verdade já foram 2 dissertações, a gente está indo para a terceira, mas eu vou destacar uma nesse contexto, que é uma função de score baseada em machine learning para docking proteína ligante. Então, esse foi um trabalho de mestrado do Oscar, onde a gente propôs essa metodologia para desenvolver uma função de score. Quando a gente está falando de desenho de funções de score baseados em machine learning, a gente precisa de dados para fazer o treinamento da função de score. Onde eu vou obter esses dados? Eu vou obter esses dados no PDBind, tá? Existem outros bancos de dados, mas nós temos utilizado o PDBind. O que é essa base de dados, tá? Ele é baseado no PDB, então ele tem um conjunto de dados de estrutura, proteína ligante, que foram, né, que tem a estrutura depositada no PDB e tem o valor experimental dessa interação calculado por algum método experimental. Então, o PDBind é um conjunto de complexos proteína ligante, os quais eu sei o valor da interação, né, o PKD experimental. Então, eu vou treinar a minha função de score baseado em machine learning usando esses dados do PDBind. Então, o PDBind tem várias versões, tem desde, não sei, 2014, a última foi o PDBind 2019, eu acho, que saiu em 2020. Então, nesse trabalho do Oscar, a gente usou várias combinações do PDBind com outras bases de dados. Tá? Então, desses complexos que eu sei o valor experimental da interação, eu vou extrair alguns descritores para treinar o meu modelo, treinar a minha função de score. O que são esses descritores? Aí pode ser, vocês podem imaginar milhões possíveis, 1D, 2D, 3D, só do ligante, só do receptor, do complexo. Aí aqui a gente pode abrir para muitas e muitas possibilidades. Então, a gente tem descritores baseados, por exemplo, o que a gente chamou de aminoácidos, né? Que no nosso caso a gente tem 20 desse tipo, que correspondem à porcentagem de aminoácidos de cada tipo na estrutura do receptor. Então, Na estrutura do receptor, eu vou verificar qual é a porcentagem de lisina, qual é a porcentagem de metionina. E esses são esses descritores que a gente chamou de AA. A gente usou BioPython para fazer esse cálculo. O segundo conjunto de descritores que a gente usou nesse trabalho foi usando o software DSSP, todas estão as referências aqui, tá? E esses descritores, eles têm principalmente informações sobre o total de resíduos do receptor, o número de cadeias. Aí são informações também do receptor. Então, essas pontes S, do tipo dos átomos SS, intra-chain, inter-chain, informações, né, entre as cadeias e dentro da cadeia, número de ligações de hidrogênio em pontes antiparalelas e paralelas, enfim, informações desse tipo, e área acessível ao solvente somente do receptor. Outros descritores que a gente pode usar para treinar nossa função de score. A gente pode usar, por exemplo, esse software, que é o Banana, tá a referência dele, tá? E esse software ele calcula que tipo de descritor. Esse vai usar descritores do ligante, do receptor e do complexo. Então, ele vai verificar contatos que tem, né, número de contatos que tem, a frequência de contatos que tem entre átomos do ligante da proteína. Então, por exemplo, se o meu átomo do meu ligante for um carbono e da minha proteína for um carbono, numa distância de 2,5 até 4 angstroms, qual é a frequência desse tipo de contato? E assim vai fazendo para vários tipos de átomo. Também tem informações eletrostáticas, informações sobre a flexibilidade do sítio, contatos hidrofóbicos, interações pi-stacking, informações só do ligante, informações do Vina, ele usa também. O Banana hoje tem uma versão que vocês podem usar na web, tanto para calcular descritores, quanto depois que vocês fizeram o docking, vocês também podem usar para fazer a análise da interação proteína-ligante, tá? Então, também ele é interessante para isso. Outro conjunto de descritores que a gente usou nesse trabalho foram descritores desse software Paddle. Ele calcula descritores 1, 2 e 3D do ligante. E aqui, nesse caso, a gente só usou 92 descritores 2D, as outras funcionalidades a gente não conseguiu usar. E aí são informações como o número de átomos pesados, número de tipos de anéis que no ligante, enfim, várias informações sobre o ligante. Um outro conjunto que é muito conhecido de descritores de biblioteca de quimioinformática, né, é o RSG. Ele gera também descritores 2D e 3D. Do RSG, ele tem muito mais descritores que a gente está usando aqui. A gente decidiu usar 147 descritores 2D e 11 3D, porque vários descritores do RSG já estavam contemplados nos outros softwares. Então, a gente usou o número de anéis alifáticos e outras informações, e 3D também. Aí a gente usou o software SASA para calcular a área acessível ao solvente, a área acessível ao BIRD, SASA também, que é a área acessível ao solvente sem e com o ligante. Daqui a gente obteve 10 descritores, e por fim a gente usou os 59 descritores do próprio Vina. Então são termos implementados no Vina, internos do Vina, para calcular o score do Vina, que a gente usou como descritores na nossa função de score. Então, no total, a gente então ficou, só para resumir para vocês, 712 descritores nesse trabalho. E aí a gente usou tudo, a gente usou Python, tanto para executar essas ferramentas, né, automatizar, calcular. Aí a gente combinamos várias entradas do PDBind, lá tem um general set, tem um refined set, que são um banco de dados um pouco mais refinado, tem várias combinações, a gente testou várias. A gente considerou como atributo-alvo para a geração da nossa função de score tanto o PKD quanto o delta PKD, que é como o delta Vina usa. A gente usou para gerar nosso modelo 2 algoritmos de regressão, que foi o Random Forest e o Gaussian Process. A gente usou uma ferramenta de seleção de atributos, porque não tinha como gerar um modelo com 712 atributos, a gente precisou usar um algoritmo de seleção. E a gente parametrizou, fizemos a escolha dos parâmetros para esses algoritmos usando o grid search. E aí a gente avaliou essas funções de score usando benchmarks que é do CASF 2013 e 2016. Para quem trabalha com docking, o CASF é bem importante de conhecer, e o artigo do CASF que descreve, né, esses benchmarks, que ele, então, tem 4 métricas para avaliar a qualidade de uma função de score, seja ela baseada em machine learning ou não. Então, esses benchmarks, eu sei que já talvez esteja passando do tempo, eu vou falar rapidamente. Esses benchmarks, a gente tem o Scoring Power, que ele é uma correlação de Pearson entre o valor que a tua função de score está predizendo e o valor experimental que tu tem lá do PD-Bind. Então, essa correlação, então é o quanto a tua função tem a habilidade de predizer um score próximo do score experimental. O Ranking Power é uma métrica que avalia a habilidade da tua função de ranquear ligantes conhecidos para um alvo. Então, nesse caso do CASF, a gente tem 57 grupinhos, né, das minhas 285 complexos que fazem parte do CASF. A gente tem alguns grupos, para cada um a gente tem até 5 ligantes, e dentro desses 5 a gente tem que ver se o ranking experimental desses 5 é igual ou o quanto a gente se difere com o ranking gerado pela função de score que a gente está propondo. O Docking Power é uma métrica que avalia a qualidade, a capacidade da função de score de identificar um ligante nativo em um conjunto de decoys que são ligantes que não existem, tá? Que são moléculas geradas artificialmente. Então, a habilidade de identificar. Então, o que acontece? Daquelas 285 complexos que fazem parte do CASF, ele gera 100 decoys para cada uma, e ele verifica se a tua função de score é capaz de predizer como melhor, né, interação, o ligante nativo em relação aos demais, né, aos ligantes que não existem. E o Screening Power, ele é a habilidade da tua função de, entre um monte de molécula, que vai ter decoys, que vai ter moléculas que não são para o teu alvo, identificar as mais promissoras. Então, como resultado, essa função de score que a gente propôs, né, aqui são funções de score que o CASF, o artigo que descreve o CASF, ele já tem calculado. Muitas dessas funções de score, a grande maioria, eu diria para vocês, é baseada em machine learning, né? Então, comparando com essas, por exemplo, o Delta Vina, ele é baseado em Random Forest, por exemplo. A nossa função, baseado no Scoring Power, a gente ficou muito próximo do Delta Vina, que era melhor, no Ranking Power também. No Docking Power, a gente ficou aqui. No Forward Screening Power, a gente ficou lá um pouco... Foi um resultado, digamos, um dos menos bons. E o nosso melhor resultado foi no Reverse Screening Power. O Reverse Screening Power é eu buscar alvo para um ligante, é o contrário. E a nossa função apresentou bons resultados para isso. E aí a gente deu continuidade nesse trabalho, de seguir usando, né, seguir estudando nesse contexto. Então, nesse trabalho aqui, que a gente deu continuidade, que é um aluno que a gente tem um mestrando, né, que é o Maurício, a gente quis avaliar diferentes algoritmos de seleção de atributos e outros algoritmos para gerar a função de score, e o efeito, né, da seleção de atributos nesses descritores. Então, a gente tinha os 712 atributos, a gente aplicou 3 algoritmos diferentes de seleção de atributos, para cada um a gente selecionou 77 atributos, e a gente avaliou, dado esses tipos de atributo, né, que eu já expliquei para vocês, o que aparecia mais frequente selecionado pelos algoritmos. Então, a gente viu, por exemplo, que os atributos de frequência de aminoácidos e o DSSP são atributos que praticamente nenhum algoritmo de seleção de atributos escolheu. Já do Banana, claro que a gente tinha 350 atributos desse tipo, vários apareceram no PCA e alguns apareceram no Random Forest no ANOVA. E assim vai, que no Vina, a maioria, atributos do Vina, né, a maioria, o ANOVA escolheu a maioria do Vina, mas o PCA escolheu só um atributo do Vina. Então, só para a gente ter uma ideia, né, de que tipo de atributo é mais frequente, foi escolhido pelos algoritmos de seleção de atributos. A gente queria entender a importância desses atributos no contexto, né, de gerar essa função de score. Aí a gente fez uma tabela com esses atributos, aqui vocês podem ter uma ideia desses 77 atributos, né, que eles aparecem. Desculpa, 77 de cada um, a gente combinou eles numa figura só, a gente ficou com um total de 188 atributos, que apareceram em pelo menos um daqueles algoritmos, né, da seleção de algum daqueles algoritmos. Então, nesse trabalho, o que a gente viu, né? Que a seleção de atributos, algoritmos de seleção de atributos, eles não convergiram para um mesmo subconjunto, variou bastante. Apareceram 188 diferentes atributos. Alguns, somente 2 apareceram selecionados pelos 3 métodos, né? A gente viu que os descritores, né, os do tipo frequência de aminoácidos gerados pelo software DSSP, eles quase não foram utilizados, então a gente praticamente vai desistir de usar esses descritores. Os descritores mais frequentes foram frequência de contatos, que é um tipo de descritor que é o que se faz nas funções de score baseada em conhecimento, é a frequência de contatos. Descritores selecionados pelo ANOVA, 33 dos 77 foram do tipo VINA, então foram obtidos do VINA. Então, esse método, por alguma razão, escolheu muitos atributos do próprio VINA, gerados pelo VINA. E somente o Random Forest, é que eu escrevi errado, selecionou o VINA Score dentro dos atributos selecionados. E esse foi o nosso resultado. O que a gente viu é que a seleção de atributos, ela influencia muito no resultado da obtenção do modelo. Então, por exemplo, aqui a gente está com 712 atributos, né, no all, e olha a qualidade, né, o Neural Networks nem roda. Os nossos 2 outros modelos tiveram resultados piores. A nossa melhor combinação, de acordo com a correlação de Pearson, aqui a gente só fez o scoring power, né, foi a combinação do Random Forest para a seleção de atributos e do Neural Networks para treinar a função de score. Né? Então, aqui o RMSE também foi o melhor resultado, que é o menor RMSE também foi para essa combinação. Então, a gente pode ver que a seleção de atributos ela tem um grande impacto nesse processo, né, de desenho de uma função de score baseada em machine learning. Aí aqui a gente tem também vários artigos de revisão mostrando outras funções de score baseada em machine learning para docking proteína ligante, tá? Eu destaco aqui o PAFNUS, que é um método baseado em deep learning, a gente estudou bastante ele aqui no laboratório. O grande diferencial dele é o input, ao invés de ser esses descritores que a gente viu aqui, né? Como é deep learning, ele vai usar outros tipos de descritores completamente diferentes que tem a ver com o complexo, a região onde está acontecendo a interação, né? Mas também ele usa para treinar o PD-bind. A grande maioria usa o PD-bind para treinar e usa o CASF para validar. Então, quem vai se aventurar nessa área vai estudar e vai usar o PD-bind, vai usar o CASF, vai usar o DUD, que é um banco de dados de decoys, né, para ver se a tua função ela identifica o ligante nativo entre decoys, vai usar muito o DUD também. E para finalizar, só algumas aplicações aqui do nosso laboratório, né, nessa área. Esse trabalho eu fiz enquanto eu estava lá na França. É uma função de score, mas baseada em conhecimento, usa técnicas de machine learning. E os 2 trabalhos que a gente submeteu agora, esse trabalho é a dissertação do Oscar. Então, gostaria de agradecer novamente o convite, agradecer aos membros do laboratório, ao professor Adriano, que coordena o grupo junto comigo, né, as agências de fomento também, e a todos os colaboradores que a gente tem no nosso grupo, né, a Rede Babel, que a gente participa, junto com a FMG, enfim. Acho que era isso.
Muito obrigada pela apresentação dos trabalhos.
Deu certo. No fim deu certo a apresentação, né? Só no início ali que travou.
Não, deu certinho.
Então, tá. Uhum.
Vou começar aqui a fazer. A gente tem 2 perguntas. Você já usou o Docker Tor? Teve alguma experiência com ele? Você comparou resultados?
O Docker Tor eu nunca usei, mas eu sempre falo dele, assim. Eu acho que ele é um ótimo software Por que eu não usei? Porque a gente tem usado sempre o Vina e a gente automatizou o Vina. Muitas vezes a gente usa conjuntos grandes de ligantes para fazer triagem virtual, e aí o Doctor, ele acho que até dá para fazer isso, mas é na web, tu tens que submeter as moléculas. Às vezes a gente trabalha com grupos que estão sintetizando ou propondo moléculas novas, então a gente acaba não podendo submetê-las num web service, a gente precisa executar local. E também pelo nosso conhecimento, assim, o uso do Vina já há muito tempo, agora até ser uma versão nova, então, mais por isso. Mas o Doctor é um ótimo software, a gente pretende começar a utilizá-la no laboratório, testar e usar com maior frequência, porque é o único, acho, software completo de docking desenvolvido no Brasil, né? Então, acho que a gente tem que usar, acho que é bem importante. E tem muitos grupos que desenvolvem funções de score, que desenvolvem outras etapas, mas um software completo, assim, eu não conheço outro, pelo menos no Brasil, assim, que seja feito. Então, pretendemos usar, mas ainda não usamos.
Mutada. Outra pergunta é porque você acredita que o Reverse Screening Power teve o melhor resultado quando comparado com os outros?
Pois é, a gente não sabe mesmo, assim. A gente não sabe. Talvez, dado os tipos de atributos que a gente está usando para treinar o modelo, né, para gerar nossa função de score, a gente não sabe exatamente qual é a razão, apesar de que a maioria das funções, né, nenhuma tem um resultado muito bom no reverse docking ali, né? A gente viu que a gente chegou lá em 18%, mas a razão especificamente eu creio que é por causa dos atributos que a gente usou para treinar. Por alguma razão, provavelmente eles usam vários do próprio receptor, e aí ajudou ao reverse docking dar mais certo.
Beleza, Karina. Essas eram as únicas perguntas. Muito obrigada pela apresentação novamente, pela presença aqui no workshop.
Então, tá. Muito obrigada, pessoal. Boa tarde. Parabéns pelo evento.
Obrigada. Agora, então, eu vou chamar a Gisele para fazer o encerramento do workshop. A gente vai voltar pro inglês, então. Pode ir, Gisele.
So the SIG Machine Learning Bioinformatics is coming to the end. We really hope you have enjoyed our event. Thank you so much for the day. We would like to thank all the attendees, our partners, the International Student Council of ISTB, AB3C, and especially our speakers who presented fascinating content and excellent discussion about the machine learning. So, and now for the best oral presentation award, elected by a scientific committee, the award goes to Rafael dos Santos Peixoto, with the work with cell segmentation for Young's special resolution through morphology analysis. Congratulations, Rafael. We will contact you soon. Just to remember that the certificate of participation will be sent with 40 days after the event. To receive yours, you need to fill the forms that will be sent in the chat, and that is available in your website, okay? It's going to be open only until the day of the event. This event was organized by RSG Brazil, a non-profit organization of students on bioinformatics. Be aware that it's open to new members. So if you want to know more or be part of it, please contact us. And then thank you for staying here today with us. Thank all participants, all attendees, all speakers.